Do we want, ready? All right, so we're going to do the unit 5, your final unit, electronically controlled transmissions, and we're adding diagnosis in there. So we can do diagnosis on our hydraulically controlled transmissions. What do you think that looks like?
Line pressure testing.
Yeah, a lot of pressure testing and road testing. The electronically controlled transmission, to me, is actually easier to diagnose. You can get more information right from the scan tool. And I'm going to say probably more than 9 out of 10 times, if you have a problem, it's mostly going to be DTC based. Okay, so as we go through this, keep that in mind. You wouldn't just randomly start checking some of these sensors and some of these solenoids. You'd most likely be getting a DTC for it, and then you'd be pursuing that DTC. Okay. So first thing, back in the day, they were hydraulic, like we talked about. That was more simple. Basically, during like the late 80s and early 90s, they started shifting more to electronic. That meant for the first time we started using a computer. It was a very basic computer, but a computer. And the main reason, fuel economy. And the benefit was we can control the transmission more precisely. So before, remember we had like the line pressure would feed a bunch of stuff. We'd have the throttle pressure. We'd have the governor pressure, right? We just had several different pressures doing what they were supposed to do, and they worked okay. But if you wanted a transmission to be able to function differently, you'd have to go inside the transmission and adjust some things. You know, adjust your throttle, adjust your governor, maybe fine tune the governor or whatever. You couldn't do that on the fly. So as soon as we get into computer controls, we're able to do a lot of stuff. That would include if the ECM can detect that the transmission is slipping, it can actually perform some level of adaptation to minimize the slip to make it last longer. Once a transmission starts to slip, your clutches are slipping like this, right? So they're wearing out. So how could you make them slip less? Think of something. More pressure, exactly. So once we computer control it and we see a slip, we can, do some adaptation and actually increase the pressure. So really the electronically controlled transmission is going to be superior. So here's some more of the reasons. It can better predict load changes. So let's just say on an older transmission, all we had was the throttle, either the throttle valve by a cable, or we had vacuum modulator. That pretty much tells you load, but when you can have a newer system that's going to look at your mass airflow, it's going to look at your throttle position. It might even also look at your throttle position separately from your accelerator pedal position. And it can look at your map sensor. It can look at all these things and better anticipate, when it can shift, when it should shift to try to give you what it wants. Cool. And then what do you think about more precise shift controls? What do you think that means? More precise. Well, let's say that you're trying to go as fast as you can. It can very precisely monitor your output shaft speed, and it can very precisely control exactly when the shift occurs. So before we would try to get close to red line. Now we can get right to red line. And if we run it right to red line, that keeps us in our power range a little bit longer, right? So it's just going to be better for power. It's going to feel more crisp, but we can also shift it a lot faster too. So before, we'd have to wait for our governor pressure to overcome our throttle pressure. Now we can really simply send a very quick signal to a shift solenoid, and the shift solenoid initiates the shift right then and there. It's much faster. And then additionally, this is a pretty cool benefit. The shift timing can be varied in different drive modes. What do you think that means? All right, you guys have driven some Supras, or at least seen somebody who has, right? You ever notice it drives totally different if you put it in sport mode? So if you're in regular mode, it's kind of early, softer shifts. You put it in some sort, in a performance or sport mode, whether a Supra or another car, it can change when it shifts. It can change how it feels when it shifts. So back in the day, you'd have to make a choice. When you built your transmission, you'd say, do we want mushy shifts, or do we want like crisp, break grandma's neck shifts? Which one you want? Well, I kind of want both. I want to be able to change back and forth as I please. Electronically controlled offers us that. We can run 2 totally different shift patterns, different programs, everything. And the main concern, though, from the government is lower emissions and better fuel economy. These are the 2 big ones. For customers, they care about this one. They don't really care about this one, typically. Some do, but most of them don't. I haven't really seen a customer come in and say, I only want to buy a super ultra low emissions rated vehicle. Let me see the California Air Resource Board certification. They don't say that. They do want to know how many MPGs though, see? So when you want to talk about lower emissions, we discussed something about the torque converter a couple weeks ago. Remember we would go with that torque converter lockup. As soon as we go computer controlled, we allow for torque converter lockup. We can do, from there, we could do flex lockup. Additionally, when we started getting into this, we can vary our shift timing really precisely to maximize our fuel economy and emissions. But pretty quickly from there, we went, for a long time, transmissions were 4 speeds. And then when we got more into this, they started stacking more and more and more. 6 speeds, 8 speeds, 10 speeds, even 11 speed. Okay, so that's the main reason that we went to electronic. Additionally, there's another side benefit. The transmissions can be lighter, like lighter duty. They don't have to be quite as beefed up because computer controls can reduce the amount of torque flowing through a transmission. So that's something called torque management. So if you get into engine performance, if let's say you had, we'll go with, this isn't really true, but it's a good example. Let's say you were to go with the Camry and then you were to go with the TRD Camry, it's got some more horsepower. They could actually basically limit the torque of the engine so that it doesn't damage the transmission. So it's kind of like, it doesn't really make a lot of sense because you're cutting engine power, but even still, you don't necessarily have to build that transmission to take all that power. You can limit the amount of torque that engine makes in certain RPMs because it's a little hard on the transmission. So it's kind of like, it's a way to save money basically for the manufacturer. Okay, coming up, that we're in here now. We're in the hydraulic control unit like we were. So basically, I'm talking valve body. But on this one, you'll notice, see these right here? You know what those are? Shift solenoids, yeah. So shift solenoids do the work. Before, the valves did the work, but the valves were controlled by hydraulics. Now the valves do the work, but the valves are controlled by the shift solenoids. Make sense? What are the shift solenoids controlled by?
ECU.
Yeah, some sort of ECU. It could be the TCM, could be the ECM, could be a PCM, but it's going to be computer controlled one way or another. Cool. And then also, remember the ECU maintains, as you can see, onboard diagnostics. So that's why I say when you're diagnosing the electronic, a lot of times you're really going after DTCs. It runs its own tests. It's testing itself. It's monitoring its circuits. It's monitoring speeds. If something is out of parameter, it sets a code. If it sets a code, we diagnose the code. And then, typically that's how we fix it. That doesn't mean that there can't be mechanical issues, but even a slipping clutch will set a code. They just might word it weird. They might say like, 3rd gear incorrect ratio. Basically what they should say is 3rd gear slipping. A holding component in 3rd gear is slipping. So back in the day in a hydraulic, right, you'd have to go out there and you'd have to drive it, you have to beat up on it, and then you'd be like, oh yeah, it slips in 3rd. Well, you can still do that, but also the onboard diagnostic systems is watching its speed sensors and detecting any slip already anyway. Make sense? So to me, I find it nicer to diagnose. Okay, so what's happening in there? It's the planetary gear, the holding devices, so your clutches, your bands, your one-way clutches, your brakes, all the same. What's the main difference? ECU is looking at sensors. Those are inputs, remember? The ECU itself is like the processing. And then the solenoids are the outputs. So this is not the first time you've heard this. Inputs, process, outputs, remember those? When's the first time you learned about it? Do you remember? Give me one other time at least.
They put it in
How about ABS, right? You remember ABS? The wheel speed sensors monitor the wheel speed. If they see an excessive amount of slip, they report that to the ECU. The ECU interprets it. The ECU says, oh, the front left brake is locked up. Let me isolate it. You power up the isolation valve. The isolation valve is moved by a solenoid, right? You learned input, process, output already. You learned it with AC, definitely learned it with brakes. You learned it electrical. But in this case, this is going to be very specific, transmission flavored input, process, output. And then the sensors, so we're going to spend quite a bit of time on sensors, right? The solenoids, we're going to talk about outputs a lot, and the sensors we're going to talk about quite a bit too. So they could monitor gear position, vehicle speed, throttle position, input and output shaft speeds. So let's break each one of those down a little bit, one by one. Gear position, I think you mostly understand. That could be as simple as a range switch that tells you where your manual valve is. Vehicle speed, let's think about that. On a hydraulically controlled transmission, what indicated vehicle speed? Exactly. So we had a governor, and now we've eliminated the governor, and we've gotten a vehicle speed sensor instead. Not a really hard concept. Now additionally, throttle position. What did the hydraulic one used to have? Yeah, the throttle cable that controlled the throttle valve. Or it might have had a vacuum modulator. But either way, let's just take a moment. We had a governor, we had a throttle valve. Do you remember how they would fight to move the shift solenoid? Remember that? Basically, that was a physical fight. That was like literally throttle pressure was pushing, governor pressure was pushing, and the throttle valve would just go with whichever was higher pressure, right? Now, that fight has basically become like a digital battle. It's more like it's like, that was actual Mortal Kombat, and this is now like Mortal Kombat through Sega, whatever. But I don't even know, the PlayStation 5. Am I right? Or no? It's 5, I'm pretty sure. So now you have the vehicle speed sensor that's indicating speed through waveform, and they're going to basically give that a score. And then you have throttle position, which is voltage, and they're going to basically give that a score. And eventually, your vehicle speed waveform will get a higher score than your throttle position, TPS, and it'll say, okay, give us an upshift. Those two never made pressure. There is no throttle pressure, do you understand? There is no governor pressure. All they do is they compare their signals digitally, and then you'd actually, technically, you could go, you couldn't as a technician, but if you wanted to be a tuner and you went into that table, you could adjust those values and you could change your shift times, and you would basically rewrite when the shifts occur. You could give a little bit of an advantage to throttle, and that way it delays all your shifts. You could give a little bit of an advantage to governor, and that would make all your shifts a little bit earlier, right? So you can go in and you can fine tune that. Typically, we don't do that. Who do you think does that? The tuner would do it after the fact. But when you buy a car, right, we're not really in the business of modifying. We're in the business of like repairing manufacturer specified vehicles. Exactly. The engineers who design it go in there and they write the programming. They write the shift pattern. They write it in code and they get it all uploaded and stuff like that. So this opens up a whole new window to what we can do for repair. Back in the day, if it was a hydraulically controlled transmission and there was a problem, you could always fix it by replacing something or adjusting something. Now, if the vehicle comes in and it's actually normal, and the real issue is that they wrote a shift pattern, like a shift timing that the customer doesn't like, we can't fix that. You understand? You can't fix that. If the customer says, oh, when I'm wide open throttle, it runs all the way up to too high RPMs, it should shift sooner, we can't change that. That's not in our purview. An engineer would have to go in and rewrite the program. Now, if an engineer rewrote the program and published it as a TSB, you could fix the car. Do you know how you'd fix it? do a software update, you do an ECU reprogram. You'd literally plug into it. Maybe you'd look for TSBs and it would say, customer's complaint is the shifts occur too late. You'd look up, boom, you got it. It would say, hook up scan tool, download the software program from TIS or whatever. That'll go on your computer. Your computer will overwrite the existing program, and bingo, that problem is solved. It was literally solved by software. We do fix cars like that. And we'll come back to that one more time, because when we replace a transmission, there's actually some different procedures that we should do to make sure that transmission shifts perfect. And then, this is a really good one, input and output shaft speeds. Those verify the gear ratio and the holding devices. So let's just pause. We've done a whole bunch of different discussions on this before, but let's just say we make a basic transmission. Let's say first is a 4-to-1 ratio, second is a 3-to-1, third is a 2-to-1, fourth, what do you want to be fourth? Make that our 1-to-1. Fifth is a 0.75 to 1. And we'd even do sixth is a 0.60 to 1. That's our gear ratio for our 6-speed. So that means in first gear, how many times should the input shaft turn for every 1 revolution of the output shaft? Give it to me. Exactly. So if I'm saying that the input shaft speed to the output shaft speed verifies the gear ratio, that's how it does it. It literally looks at the input shaft and it says, now if you turn once, and it says output shaft, no, that's backwards. If you turn 4 times on the input, you should turn 1 time on the output. Make sense? And that's how it verifies the gear ratio. Now, if you were to remember, this is how we make our gear ratio, right? Planetary gear set. That's still all the same. So if I came over here with a brake and I was trying to hold, let's say, the ring, and I was turning the sun, but let's just say for whatever reason, my brake wasn't holding the ring as much. Do you see how this is slipping now? You might have your input shaft turn 5 times and your output shaft turn once. What does that look like to the ECU though? It is a slip, but you know what the ECU may say? Incorrect gear ratio. You'll be like, hey, your gear ratio is 5-to-1, ding dong. It's like, does that mean someone put the wrong 5th gear parts in there? Or the wrong 1st gear parts in there, I mean? You understand, this is every gear. There is no first, there's no fourth, there's just hold something and turn something and have something be turned. Make sense? So if in first gear, you're getting a 5-to-1 gear ratio, but in second gear, you're back to your 3-to-1 ratio, that would mean in first gear, some holding component is slipping. Now, how would you figure out which holding components to check? You could, and if you put it in first may or may not feel like much of a slip, but if you were to feel like it slipped, how would you know maybe which ones to suspect? You learned this last lesson, the chart, exactly. So you could still look at the chart, but the thing is the ECU is already kind of like, the ECU is monitoring for a slip at all times, and if it's slipping in first, and you got a code for incorrect gear ratio in first, you could probably go to the chart and right off the bat be like, what the heck holds in first but not any other gear? And then determine that whatever first gear clutch is slipping, whatever that thing is. The low reverse clutch is slipping, in which case reverse would probably slip too. Cool, so there's a lot of positives and advantages to being electronically controlled. That's my point. But a lot of this stuff you'll find is kind of the same. Now look what you got here. Here's that ECU. This one happens to be a PCM. So clarifying, ECM is generally engine control module. TCM is generally transmission control module. PCM is generally powertrain. However, you may find some manufacturers will say ECM and they just mean like electronic control module. Other times they'll call it the ECM, but the engine control module may control the transmission too. So it's a little fuzzy, okay? But you got to find out which computer ultimately controls the shifts. Right? And then again, it's receiving inputs. It is determining the shift timing and the firmness of the shift based on its programming. And then it will execute a task. So if that means you're at wide open throttle, it sees you're at wide open throttle, it's going to say, okay, hold off on the shifts, let's delay them till near red line, and let's firm it up. Let's ramp up line pressure. It'll increase line pressure right there on the spot, and then you'll get late firm shifts. Boom. Chirping gears, banging gears, make it pretty cool. Okay, and then here's some of the inputs. So there's a lot, but as you can see, this is Toyota specific right now. NT, for example, if you're in Toyota land, you need to know NT is input speed sensor, which is also called turbine speed, right? Because if you'll remember back to torque converters, remember the turbine thing I told you about, the turbine, which is a turbine. The turbine is in the torque converter. The turbine drives the input shaft. So you want to call it turbine, you want to call it turbine shaft, you want to call it input shaft, they're all the same. It's all the same stuff, right? That's a common one. So NT, and the type, at least on the U series, is an AC waveform. So when we look at these sensors, you should know you're going to put either your meter on AC, and you can try to measure the voltage, but that doesn't give you a real clear picture. If you really wanted to monitor that speed sensor, you'd actually go for the pico. You go for the pico, put it on AC, and then you'd actually get the oscillations, right? That sine wave style. And each oscillation will be like a tooth, and then not a tooth, and then a tooth, but they'll be rounded. And that's how the ECM sees speed. So the ECM gets that raw AC signal, converts it to a DC inside, and then makes it zeros and ones, because that's computer lingo. That's computer language, right? Similar with a counter shaft, and that would only be on a lot of the transaxles. NC2 is C2 speed sensor, so you might actually have a couple different shaft speeds in there. Sometimes they'll monitor different shaft speeds. The vehicle speed is pretty consistent. So the digital would be a Hall effect sensor. So it could be either, do you see that? It could be AC, but generally it's going to be digital, 5 volts or 12 volts. So what that means, those are going to be square waves. The digital tends to be a little more precise, a little more accurate, but the biggest thing is those AC waveforms, they're not real accurate until about 3 miles an hour. And when it's a transmission, we want to know when it's spinning as soon as it starts spinning. So you won't really see AC stuff at that point. And if you want, same with that, you could use your meter and you could put it on, some sort of setting and maybe be able to tell if it's giving some sort of signal. But if you really want to tell what's going on, you're going to have to go with some sort of oscilloscope, right? Like ASE, by the way, we'll call this a DSO. Anybody heard of a DSO? Digital storage oscilloscope. If you see DSO, you're just pretty much picturing a picoscope, just some sort of scope. When you do a picoscope, remember what you're looking for? Do you remember? The pattern? Remember how you'd see like a pattern on screen? You'd see in this case, it'd be square waves. It'd be like, oh, okay, look at those square waves. You'd be like, there's a bunch of square waves, and then there's a big break in the square waves, and then they come back. You'd be like, okay, maybe something's up with that reluctor wheel. Make sense? Or if the sensor's not reading at all, what might you see on the picoscope? Flat line, yeah. Then you'd be like, okay, cool, I know what I got, right? So generally when you get into speed sensors, you're going to realistically have to be doing picoscope work, okay? Cool. And then some of these are really nice. If we have pressure sensors, like pressure sensor 1 and pressure sensor 2, they don't all have this, but the U660s, 760s do. That would actually give you the C1 pressure and the C2 pressure, which are controlled by shift solenoid linear 1 and shift solenoid linear 2. All right, so to me, this is the ideal, because if you have a shift solenoid and the circuit's good, the ECM has no way to know if it's working or not, realistically. So they've done a little step further. Now when they command the shift solenoid on or off, and we're going to come back to the L, by the way, because the L is a little complicated. But when they command that shift solenoid on, they can actually verify that shift solenoid worked because it monitors the pressure that the shift solenoid sends to, let's say, C1. You guys remember C1? We talked about that clutch. C1 clutch, right? Like on the older ones, that was the forward clutch. So remember we were talking about how to diagnose the hydraulically controlled transmission? You'd have to, you'd have to actually put a pressure tap, right? You'd have to put a port in, you'd have to thread the pressure gauge on, and you'd measure pressure right there. And when C1 came applied, you'd be like, oh, how much pressure does C1 have? You don't have to do that because we've got a pressure sensor. You could literally look on live data at pressure sensor and be like, is C1 applied, yes or no? And how many PSI? Cool. So to me, this is the ideal diagnosis. When you have a pressure sensor that verifies the operation of your shift solenoid and that your clutch is engaged. Amazing. If you were to look at pressure sensor 1 and you were to see 140 PSI, which is your line pressure, you could look up line pressure is 140, C1 is 140, and it's slipping. What's the cause of the slip? The clutch. You don't think it's a leaking seal? You don't think it's like a hydraulic leak? Because if it was, you wouldn't be getting 140 on this pressure sensor. See what I'm saying? See how much tighter the diagnosis is when you have the pressure sensor to verify it's getting full pressure and not leaking in the valve body or leaking at a piston seal? Amazing. But we don't have them for all of them. You only get them here on C1 and C2. You're not going to generally find a whole lot of them on the various different brakes, B1, B2, B3, B4. They're like, you know what? It's too expensive to put a pressure sensor on every single circuit. Cool. And then SLU is for torque converter TCC lockup. So it monitors that individually as well to make sure that SLU is doing its job. So when SLU is commanded on, it should see throttle pressure sensor number 3 spike up. Cool. And then here's one that you might be familiar with based on today's activity. THO or OT, that's thermistor. It's like transmission temperature. O is oil. So basically ATF temperature. On the ASE, they'll call that generally TFT. Transmission fluid temperature. So if you see TFT, you got to know some acronyms. Sometimes they'll spell it out though too. They may say transmission fluid temperature. If we're going to talk about transmission fluid temperature sensor, a lot of times Toyota likes to use oil temperature or temperature of the oil. It's the same. These are all going to be thermistors. Generally, they're all going to work on a 5-volt circuit. If it's an open circuit, what's it going to read? True, but on the scan tool. Yeah, so what temperature is it going to show on live data? -40. So if you got a code for the circuit and you look in live data, you see -40, that sucker's an open. The conversation's over. If you jump in there and you see the temperature's reading 300, come on, give it back to me. That's a short. That's like no resistance in the circuit, so somehow the wire feeding the thermistor and coming back to the ECU is just jumpered in there somehow. Okay, so everything you learn about that's going to be the same. This is the same for intake air temperature, coolant temperature sensor. Thermistor circuits are really pretty easy once you get them. All right, so let's talk for a second about speed sensors. I overall want to explain very clearly why we're going to use these. So like we were talking about, here's your gear set. If your gear set is supposed to be, let's go with that 4-to-1. Picture this. It's monitoring your input speed, right? And that's why the input shaft speed sensor is right there, because this is your input shaft speed. This is your input shaft. It's turned by the turbine, so that's why they may call it a turbine shaft speed. It's just picking up these teeth on this drum. So if you look on the transmission and there's a sensor at the front, that's generally going to be your input shaft. Cool. And then how does the power get from the input to the output? Because here on the output, look, output speed sensor is right here on the output shaft. How does it get back there? right? So it's going to use various gear sets like this. It's going to turn something, it's going to hold something, and something's going to be output, and it may do that 3 times or 4 times. If that's an 8-speed, it's got 4 planetary gear sets. And each one of those planetary gear sets, we have a clutch becoming the input, right? So like on this one, in this clutch drum, one of the clutches is C1, where it connects the input shaft to, I don't remember if it connects to the sun gear. In fact, I think this is meant to be an A750, but in this example, let's say the input shaft gets connected to the sun gear via C1. Cool. Then we got to have another one. Maybe B1 is going to hold the carrier, and then the ring gear is going to become the output, right? So the output's going to drive something, but then we got to have an input, a holding, and an output on all those gear sets. So at any given time, we have a bunch of things that are grabbing and holding. Well, what if, let's go with that B2. That B2 is going to hold the carrier, right? What if B2 is letting the carrier turn a little bit? What do you think would happen? What would happen? Okay, I'll give it 2 numbers. Slip is correct. You're onto it. So let's just say this was 1,000 RPMs. If it's a 4 to 1, how much RPM should be coming out the output? 250 is correct. Okay, but let's just say, here we are, we're driving it, and all of a sudden the ECM starts to see what do you think that would feel like if you're in the driver's seat, first off? You were at 1,000, right? And now your RPMs are way up. That's what a slip feels like. Your RPMs are up and the car's not going. It's slipping. It's almost like, now I know you'd never do this on purpose, but have you ever pushed the gas so hard the tires spin and the RPMs go up, but the car no go? That's slipping. Where's the slip? Well, it may be the tires. But in this case, it's going to feel like that, except there's going to be no smoke. And your RPMs are going to be up, but your vehicle's not going faster. That feels like a slip. Well, guess what? This ECM's already way past that. The ECM's already actually calculated the gear ratio. What's the gear ratio here? What's the gear ratio at that? Ready? 10 to 1. Your first gear should not be 10 to 1. Make sense? How is the first gear 10 to 1? In this example, C1 is slipping. Cool? Do you understand what we really use the input and output shaft speed sensors for? They really only have one job. It's just to monitor if it's slipping or not. Cool? You like it? Is it because someone put the wrong pinions in there? The first gear pinions are incorrect in here? No. It's because one of the holding components, such as C1, or B, I think it was B1. I meant to say B1 that was holding the carrier. That would be slipping. Cool? Very good on the input-output shaft speed. You need to be. Bonus question. You guys remember torque converters? How does it measure the torque converter clutch lockup? Give you a clue. This sensor is one of that. That's part of that equation. What's the other one? Which one? Good guess. But the input and the output are measuring what's between them. Where's the torque converter? It's over here, huh? The crank, exactly. It'll use engine RPM from the crankshaft position sensor and input shaft speed sensor, and they should be different, but not when the torque converter clutch is locked up. They should be 1-to-1 at that point, right? So really with just crank speed, input speed, output speed, we can monitor the torque converter clutch, and we can monitor all the clutches and bands and brakes and one-way clutches and everything in here. Cool? There will be questions on the ASE about that. I'm telling you right now. It's going to give you different RPMs. It may give you different RPMs between the crank and the input. That would be TCC. It may give you different RPMs between the input and output. That would be holding devices related to the planetary gear sets, but it might only be in certain gears, so you know. Cool? And also, we focus a lot on the electrical, but I want to focus for a second on the mechanical. If there's something wrong with this drum, defects on this drum will cause defects on this sensor. Make sense? Like, let's say this is reading off this toothed wheel, but this toothed wheel cracks and breaks off. It's going to read 0 RPMs, even though it's spinning. The reluctor wheel could be damaged. Okay, so keep those in mind too. All right, and then how it goes from there. A lot of these speed sensors, they can vary. There's a lot of different types. And a lot of times, unfortunately, they go from the transaxle to the combination meter. And the combination meter will give a signal to the ECM. So that's a little old school, but some still work like that, you found, huh? Unfortunately, that's just the way it is. On a lot of newer stuff, though, they'll just send the speed sensor directly to the TCM, and then the TCM will multiplex it to any computer that needs to know. You know, they'll basically, the initial speed will go to the module, and then the module will send it to the instrument cluster via CAN network. But it could be this way too. And they could look all kinds of different ways. This one's a vehicle speed sensor being driven right off the diff. That's what these swirly looking gears are there. That's to drive this speed sensor. All right, here's something really hilarious. That governor, remember I actually was showing you parts of the governor? This is literally a governor, and it would drop in there. When the speed sensors first came out, it actually had the bottom of a governor. If you look, these look the same, right? Kind of the same. One's a little more worn. They had the bottom of the governor, which this one's worn. This is called Apple Core wear. This governor shot, but the governor would spin, and then they're like, forget that. We'll put a speed sensor in there. And it looked the same and it worked the same, but rather than spinning weights, this same little plastic gear would spin and it would generate a signal on this vehicle speed sensor. Vehicle speed sensor tends to be on a transaxle because they measure it right off the diff, off the final drive. Whereas in a rear wheel drive, they tend to more be like an output shaft. This is not vehicle speed because it still has to go through the axle that's back there that's going to give it its final reduction. So mostly they're the same, but one of them is really output shaft and one of them is actually vehicle speed. Make sense? All right, and again, they can vary. So like, here's one for example. This VSS is a little more new. It's a little more modernized. It's not this type that spins and has a plastic gear. This is old school junk. This is actually going to be a real Hall effect sensor. And it's not going to actually touch, but it's going to sense the tooth, not sense the tooth, sense the tooth, not sense the tooth, right? That'd be more typical. They could be, though, an ASE type, reluctance type sensor. If it's, depending on the type, they're all going to have different waveforms, though. Okay, so like a lot of times, what you're going to mostly see would be more like a square wave. So there's a tooth next to the sensor, no tooth next to the sensor. Tooth next to the sensor, no tooth next to the sensor. Tooth next to the sensor, etc. Now, if I were to go this way, there's a couple different ways that they can do this, but a lot of times these sensors can also tell if it's going backwards. So depending on the exact type, I've seen some interesting things. If they have a double wide, either low spot or high spot, that means they're also telling position, right? So if all you have is equal squares, you never know where it's at. But if you have one that's got like maybe a double low, and then let's even just say a double high, and then a single. If you think about it, if the ECM sees the double high and then the double low, it knows it's forward. But if it's backward, what's it going to see? The double low, then the double high. Cool. So they'll do some different things. They'll also do various different things with like a magnetic strip where it can indicate forward or back. But they want to know forward and back. They want to know speed. They may want to know position as well. But ultimately, this is your vehicle speed right there. It's those squares. As it speeds up, what's it going to look like? right? That would be going a lot faster. And the TCM will know that. All right, so let's say that you have DTC for a vehicle speed sensor. There's some tests you can do, but ultimately you may end up needing to do, get the picoscope on there and pull a waveform to get the whole picture of what you got. It's not rocket science though. Cool, but on this type, this is just 2 wires. As this reluctor spins, right, you see these teeth, right? This one actually may not look like that, by the way. This one's more likely to look more like this. This is a tooth, that's not a tooth. But this is AC, so this would be 0. So this would be like a positive 1 volt. This would be like a negative 1 volt. Or whatever the voltage is, make sense? But it generates its own voltage. So just 2 wires. The faster you spin, the more it'll be. You might get like to maybe 1.5. But you'll also get these closer together because it's up and down faster. Right, so that would be your basic magnetic pickup type speed sensor. Cool. And then this is a little more similar to a Hall effect type switch. So a lot of times what they'll do a reed switch, and every time the magnet is actually on the spinning rotor, every time the magnet comes by, it'll actually close this switch. And when it does, that'll a lot of times drop it to negative. And then when it goes by, this will open back up, that'll bring it to positive, time will go by, the next tooth comes by, drops it to negative, right? So that would be an example of a square wave. It could be either one. You could see the difference between AC and DC, right? AC's round, DC's square. This one, again, you could try to use your meter. Some of the meters, like a nice Fluke, will have an RPM function, and it'll actually measure, it'll give you a number, and as you speed up, that number will go up, but you're not really, in other words, if you had a damaged magnet right here, on the waveform, that might look like, right? So like you could see that on a picoscope. On your meter, you'll miss it. You'll be like, I have no idea what's wrong with this. When you put a scope on it, you'll be like, oh, I see that. That magnet in there is broken or something. Okay, so that's again why I'm plugging for the picoscope or some sort of oscilloscope. Then here's the input shaft speed. You can see it could also be the turbine speed sensor. Where is it at? It's going to be somewhere in the bell housing. Or generally in the front of the transmission. And they could be any of those types. Could be the magnetic pickup, that's AC. Could be the reed type, that's DC. Again, you're going to see more and more Hall effect, which is just more of like a AC waveform. Cool. And now, this is going to give you some kind of interesting. It's the first time you're going to hear this, but there's something on the ASE a lot of times called clutch volume index. So if you remember, this is kind of what I showed you before. If you'll remember, the input shaft to the output shaft is monitoring the gear ratio. If the gear ratio is incorrect, it basically means there's a slip, right? It's saying 3.3 to 1 ratio error, whatever, because it's 3,000 RPMs and 900. Cool, that sets a code. Boom. But what's interesting is, if you think about it, when the customer jumps in, let's make this a little bit different than Toyota. Let's say it's a Chrysler. Pick a Chrysler model that you like. Wow, like that? Nothing?
Chrysler 300?
Chrysler 300 it is. Whoever drives those cars, they always drive them like they're stolen, don't they?
Yeah.
They do. So I know why you're thinking somebody cut you off. All right. They cut you off in this Chrysler 300, and then they return it to the lot because they were just test driving it to see if they wanted to buy it. They didn't buy it because this transmission shifted totally different than this one. That would be like a bad thing, right? So when the manufacturer makes these transmissions, the housings and stuff are cast at different plants. There can be a little bit of different clutch clearances. So if you had a clutch pack clearance, right? We'll even draw some quick clutches and steels. There's a couple lessons here. I'll do it like this. Clutches and steels, right? And then in the bore, in the housing, this has got a certain amount that it can move in the actual piston bore. And if you look right here, that's how much movement it has. And let's just say it's a 100 thousandths. Cool. When we send fluid to that piston, it's got to lift these clutches and squeeze them. How much did it have to lift them? We measured the clearance right there, right? If you were to put a dial indicator here and air check it, thunk, and then let the air out, thunk, thunk, 100 thousandths. It's going to take some time to lift that piston 100 thousandths, right? Because it's got to move a certain volume of fluid. Now let's just say we built another one, and another one only had 60 thousandths. Which one would have a quicker shift? Not to say that it shifts sooner, but once the shift initiates, right? Once shift solenoid 1 says, yeah, send fluid to that pressure, which one is going to engage the clutches quicker? Exactly. So from the manufacturer, you may have a range of 60 to 100 thousandths when you rebuild that transmission, and you'd measure it with a dial indicator. If one is set at 60 and one is set at 100, they're going to shift different. The customers don't want them to shift different. Every Chrysler 300 in that year should shift the same. How could we make them all shift the same? What do you think? You could make them all mechanically the same, but see, then you're talking about someone spending more time getting them exactly right, because maybe this lower flange right here, this lower one, can be different thicknesses, and if you want a different thickness, I switch the caps. If you want a different thickness, now we got to spend more time to get it perfect. It's actually cheaper to let it be varied between 60 and 100. And then you do something right here called a clutch volume index adjustment. So totally dropped that cap. So if we were to go ahead and drive this vehicle, and it were to see, hey, this particular vehicle, let's say it's the 100, this particular vehicle took a little bit of time to apply this clutch. Let's actually use a variable solenoid, and let's have that solenoid ramp up faster and send more volume of fluid, right? Clutch volume index. There's more volume on the 100 thousandths clearance, so it will actually vary the solenoid and send more fluid to get it to shift just like the one that's a 60 thousandths. All right, so if you understood all that, you understand it's monitoring a number of things. It's not necessarily monitoring pressure. It's going to monitor your input and output shaft speed. By the time it lets go of first and it gets ready to apply some different holding component in second, there's an amount of time where your engine RPM is going up and your transmission output shaft is going down. It's saying hey, that clutch isn't engaged. So it can look at your input and output shaft speed and then say, okay, this one shifts kind of slow. Let's ramp up the clutch volume index. So when the car is brand new, it may have kind of a slower filling clutch volume index. And as it wears the clutches today, tomorrow, next year, the year after, and 5 years from now, you're going to get more and more closer from the 60 to the 100, right? You're going to have more clearance here. On the old cars, it would start to have a little bit of a sloppy shift. On the new cars, it'll keep it primo because it'll basically adapt it. CVI is a Chrysler term. GM's term is TAP, transmission adapt pressures. All the manufacturers do some sort of adaptation to get the transmission to shift how it's supposed to shift. Watching this, do you understand? All right, so let's just say, hypothetically, you yank that transmission out of there that had 100, and you slam one in there that has 60, and you don't do anything with the ECM, how are those shifts going to be? They're going to be too fast. They might even feel a little bit harsh. All right, so what do you think the ECU should do? It should start chilling out, right? So it will do some clutch volume index adaptation. It will do transmission adapt pressure adaptation. Even the Toyotas do too. But the proper procedure, if you change the transmission, you're supposed to manually reset that in the scan tool. Reset clutch volume index. So if you got a question about a customer a technician replaces a transmission and after that it's kind of hard shifting, it may just be as simple as like they're supposed to reset that. We, us, not they, them. Me, I, us, you need to reset. Make sense? Transmission, reset, reset. And then you're actually supposed to drive it and it's going to adapt a little bit. And you can feel after 4 or 5 shifts, you can actually tell a pretty big difference. Then the customer gets it and everything's good, right? That's good service. Now Toyota does it a bit different and it comes up a little bit later. Toyota doesn't have they may have a reset on some, but most of the time they don't. What they have is a whole series of digits you put in. On the outside of the transmission, there's a weird box. It looks like a checkered, it's white, black, white, black, white. It's like a checkered flag. It's got a bunch of numbers and letters. You blast in all those numbers and letters and it's under, I think it's under utility. And that's going to automatically adapt. It's going to automatically set the correct adaptation numbers right off the bat. You don't even have to drive it. So when they do the transmission, they do all the measurements. And then those measurements basically correlate to a number. When you put that number in there, it knows if it's closer to the 60,000s or if it's closer to the 100. So it's kind of interesting. But they'll all have some level of adaptation. Okay? And that is a pretty cool feature, I think. And then again, we're also going to use the crankshaft position sensor. Renee figured out why, right? For that bonus question to monitor torque converter lockup. Cool. And that's kind of what this was saying. Talking about the TCC, how long does it take? You know, is it actually locking up all the way, and etc. Now look at this, transition fluid temperature sensor. What is it? Thermistor, okay? So if you think you understand thermistors, cool. But if you don't, I'm gonna try to help you. So here's your, let's call this a TCM. TCM has 5 volts. TCM sends 5 volts. It goes through a fixed resistor and then it comes out. Okay? But we put a little sense wire on here. Can you see that? That's a sense wire on there. Then we're going to send it through a thermistor. That's a variable resistor, thermistor. And then we're going to bring this back and we'll ground it in the ECU. All right? Right there, if you understand how this works, you can do any DTC at all related to temperature sensor, especially transmission fluid. It's not going to be that tough. So let's just say we had an open right there. Scan tool reading will be a -40. The problem is you don't know if the open is here, 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 here. You don't know. Am I right? You just know it has an open. So if the TCM sets a transmission fluid temperature sensor circuit open or short to ground or whatever, you know there's a problem in the circuit, right? But basically what you need to know is, am I selling a TCM? Am I selling a harness or wire repair? Or am I selling a transition fluid temperature sensor? Or like in Toyota land, if it's, you know, I was joking around, but honestly, if that problem is inside the transmission, we're going to sell generally a transmission, literally. If it's a pretty new car and you know, we're feeling like you want to go in there, I think if you explained, hey, I measured it, I know that it's an open circuit in the transmission fluid temperature sensor, I want to drain the fluid, I want to pull the pan, I want to fix the sensor, which by the way, I was carrying this harness around just for this. It's this simple, so you know, this right here, this little thing right there, that is your transition fluid temperature sensor. You can't replace this one, you actually have to replace this harness. But if you really wanted to, you could go in there and fix that. You just have to really word it well, okay? So And it also could be one of these wires, right? These wires were orange. So it could be one of these wires. It could even be like a pin fit issue, right? So if these are the female pins and they're kind of opened up and the male pin is no longer really making good contact, that can give you the open circuit as well. So it could be a fairly minor repair, but to do this, you understand you're going to be in the valve body. Sometimes you have to actually pull the valve body off to get certain parts out. So either way, you mostly need to know, is it inside? And if it's inside, is it the sensor or is it one of the little wires? In this case, it doesn't really matter because they come together. It's an assembly. So basically, keep it simple, stupid method. You're selling a computer, you're selling a harness, or you're selling a transmission. You don't even have to be a sharpshooter, but like I'll read you a literal true story, and it's actually related to that last subject we're talking about. Oh, I can't, my phone's there, so I got to remember it. Okay, this was, I'm not going to name names, but someone texted me and said, hey, I got a guy with a question, his transmission won't shift out of first, it just goes first. And he took it to the mechanic, and the mechanic said, oh yeah, you need a new transmission. So he put a transmission in. And with the new used transmission, it goes first. It won't shift into second. So what do you think? Put one more in, just in case the first one failed and the random one out of the junkyard happened to have the exact same failure internally. Does that sound likely? You all been inside a transmission. Do you think they have the identical tiny problem inside there? It's just not likely. But yes, he literally said put another one in, and this customer did it. So it's had the original transmission, a new used one, and now it's got another new used one. So there's been 3 of them, and guess what? First. So he asked and said, what should I tell? What should this guy do? And I just said, well, it's an electronically controlled transmission. So like it's going to be either an input problem, right? Inputs are sensors, a processing problem, which would be the ECU, or an output problem. And the outputs are shift solenoids. And the processor is the ECM. But the inputs, there's a bunch of different ones. Now, you listening to that, don't you think you'd start with like check for codes? And I didn't get any more involved in that, but I said the first thing you want to do is check for codes. You're probably going to be seeing something for vehicle speed sensor, and you need to check for codes like on all the modules. Because sometimes the vehicle speed sensor, they might actually use like a wheel speed sensor, send that to the ABS unit, then the ABS unit may send that on the CAN network to control the upshift, right? So like you gotta really know how to do the diagnosis. You don't just say, oh, it's got a code, let me replace the transmission. Cool? Now we'll break this down. If you really wanted to know how this works, let's just say we were doing some measurements before. Does anybody remember what the spec was for a transition fluid temperature sensor? Okay, let's make it simple. 100 ohms. How about that? Let's go like this. If this was a 100 ohm resistor inside, see that? 100 ohms. And let's just say our variable resistor, which is the thermistor, was 100 ohms. Right? That'd be in spec, right? Maybe 100 ohms means about 126 degrees or something. I don't know. If we had 5 volts coming in, we had a 100 ohm resistor here, we had a 100 ohm resistor here, what is it measuring on the sense wire? Want me to break it down? You want to do 2.5 is right. Mata, you paid attention in AC, didn't you? We covered this in AC. This is review. How do you know it? All right, I like to explain it like you got parents, right? Parents got $5. $5 used to get you a lot. Don't get you much now. Don't spend it all in one place. $5 gets passed down to 2, let's just say brothers. In this case, this brother has 100 ohms of strength, and this brother has 100 ohms of strength. Well, who do you think wins? It's a tie, so split the money. How much do they get each? $2.50 a piece. Don't spend it all in one place, okay? And that's how I'm saying, if this were to drop 2.5 volts, your sense wire in green would show, right over here, 2.5 volts. If it reads 2.5 volts, it knows the resistance of that variable resistor. The way I was taught in school was incorrect. It wouldn't stop me from diagnosing the car, so like I'm good, but technically it was wrong. I was told, yeah, your ECM puts a ohm meter right here and it measures the resistance of the circuit. Not really. No, it doesn't. It's a voltage divider circuit. It sends 5 volts, sends it through a 100 ohm resistor, and it measures what the voltage is after. It'll give you the same result as measuring resistance. Follow what I'm saying? All right, now let's switch it up. Let's just say, and by the way, this didn't have an open, but now it has an open, a smudged open. Now it's a clean open. Now what's it going to read on the sense circuit? You're right. How'd you know? Right, so this is kind of what I was explaining in SpongeBob electrical class. If this is a traffic accident, it's a resistor, right? Remember that? Normally the resistor would slow the cars down. It would basically drop the amperage and it would drop voltage right there. But see, the problem is there's a big open right here. So even if this is a car accident, all the cars will go right past the accident and they'll just be waiting. You know what they say when they're sitting right here? I'm ready. I'm ready. I'm ready. No? See, you guys would like firmly grasp it better. Okay. But now that you see, this has infinite resistance right here. You remember in our meter, if you were to measure this right here, what would it read? From here to here. That would measure OL, am I right? OL is like more than millions of ohms. That's like a ton of resistance. So now if I'm saying this big brother right there has infinite amounts of ohms power, how much is the first little brother going to take right here? I don't think so. It's going to take nothing, right? This huge one down here is going to take it all. This one takes nothing, so 5 volts will go right through. $5 all goes to the big brother with the infinite power. Makes sense? Infinite power will take all $5. Little brother gets nothing. It doesn't consume anything. It goes right by. So if your sense wire reads a 5 volts, it automatically knows it's an open and it will read a -40. Cool? 5 volts is -40. .5 volts is 126. Cool, you picking up what I'm putting down? Kind of, sort of? We'll do one more just so you're very thorough. Let's just say on transmission assembly, we put the valve body back on and we clamp these 2 wires together right here. And now it just does this. Any ideas what that one's going to read? That is a short. So what's it going to read? What do you think? 3, yeah, on there, exactly. So we're going to make that one orange. It's going to read 300 degrees. So that's a full short. There's no resistance in that circuit. Now, how's that going to work right here? If this resistor is 100 ohms, what's this resistor? Nothing. So this one has no power, and this one has 100 ohms. So this one's literally going to drop all the voltage. This one has 100 ohms, and this one has nothing. Do you understand? So what's the reading going to be on the sense wire? Make sense? So now do you understand how the ECM, it uses voltage drop to determine resistance. Now when we come in, the way we're going to diagnose it is different. Now you guys could see, I could bust the meter out if you'd like. I'll bust the meter out temporarily, and then I'm going to revert over to markers. All right, so if I were to use the meter, matter of fact, I'll use the clamps. How about that, right? Here's my meter leads, like this, okay? If I were to take my red lead and put it here, and my black lead and put it here, what would my resistance be? Exactly, it'd be perfect continuity. There'd be no resistance. See, then I'd be like, oh yeah, there's a short. The thing is, let's just say the transmission is down here. And as far as you know, these are connected, right? Because if you can see that the wire is looped, you don't even need to get the meter out. But if I read 0 ohms right here, where's the problem? Maybe, but you don't know that, do you? Because it could be here, it could be here, or it could be here. So if I read 0 ohms right here, what would I do next? How about this? What if I measured 0 ohms right here and I disconnected this? I'd have to isolate it and disconnect that. Then I would know it's in the transmission, right? But if I measured 0 ohms here and then I came down here and I measured 100 ohms, what would that tell me? Not in the transmission. Exactly. So now what should I do? What should I get? Like 0, 0.2 maybe. If let's say I got 0.2, what should I do next? Let's say I got OL. Needs a harness, right? You can. It's up to you. And that's what's kind of cool about this is if you know what to do, you don't necessarily have to follow TIS to a T. That's why when you guys busted out your diagnostic stuff, I'm kind of like, no, just pull the diagram up. Because it has you doing all sorts of stuff. Like what it'll have you do is like measure this resistance, and then it'll say like measure from this to ground to see if it's shorted, and then it's like now measure this one to ground to see if it's shorted. It should be at least 10 ohms, and then it's sort of like measure this to voltage and see if it's shorted, and then measure this to voltage and see if it's shorted. And I'm like, just chill out. Like how many tests are you going to do? The engineers tend to be really heavy on like, is it shorted to voltage or is it shorted to ground? Like most of the time, you know what it is? It's chewed, it's cut, it's a loose terminal, it's corroded. Like the shorts can happen, but I would if I first checked and it was like OL, well, in fact, if it was shorted, it wouldn't even be OL. So like if it's OL, I'm not real nervous about it. See what I'm saying? It's kind of weird, but that's how I would keep it simple, stupid. That's how you diagnose any temperature sensor. Cool? Now, we must continue on. So if you were to get a temperature sensor circuit code, what do you think the transmission would do? Because it's going to put it in some sort of a mode and it might bang gears, right? Same with like if you had a problem with the output shaft speed sensor, it may not actually shift. So each of these things that we talk about, remember, it'll have a certain outcome. It'll make it do something. All right, how about this one? So this is kind of what we described. The PCM will vary the shift timing and pressure based upon the transmission fluid temperature. So if transmission fluid is cold, we don't really want it to shift that hard. We may not really want it to go to red line. We may shift a little bit earlier. By the way, if the transmission fluid temperature gets hot, that can also lock up the TCC clutch. It can vary your shift timing. It can also increase your line pressure to make sure no clutches are slipping and making more heat. It can even be an input to the engine control module to run the cooling fan. So this TFT is an important sensor. Cool, obviously we use the scan tool. Here's that TFT right there. Look familiar? This is literally the harness with the sensor right there. That's it in the valve body. Pretty typical. Now engine coolant, similar, and we don't need to spend quite as much time, but what it will say, it'll show you the resistance spec. So if we were to have, let's say, 104 degrees, if I can draw straight, it should be somewhere in this range. So 2 ohms, and it's usually 100 ohms, but let's go with, yeah, we'll make it 100. Or it could be as high as maybe, if we were to continue this line, 4. So let's say between 200 ohms to 400 ohms if it is 104. But what if it's 212? Interesting. So 212 is going to be about 0.400, so that's 40 ohms, to about like maybe 50 ohms. You understand? So when you measure the resistance, it's not just is it in spec, it's does it correlate with the temperature. So now here I'm going to give you a good old flat rado hack. If I roll out to the car and I want to know if the transmission fluid temperature sensor is reading accurately, you know what I'm going to do? Car's been sitting all day. I'm not going to start it. I'm going to do key on, engine off. I'm going to look at intake air, coolant temperature, and transmission fluid temperature. What should they all be? Ambient. They should all be at least the same. Whatever the ambient, it's been sitting all day, right? So boom, right off the bat, I already got the car half diagnosed. So this is important when there's a problem, but don't jump to this and be like, oh, to check that sensor, I need to get TIS and I need to get all these specs and you get all this. Like, just go about it in a much more practical way and just check the live data at ambient temperature. Now, if it's off, then yeah, you may need to do more of this type of stuff. Cool? So that's how all those thermistors work. Now, why do you think engine coolant temperature is part of transmission diagnosis? Do you think the transmission is going to shift the same if it's cold engine versus fully warmed up? Exactly, because we don't want it to shift the same if it's cold engine. So this can have an effect on a vehicle. Now, I'll tell you, there was one very interesting concept on there, and I don't remember the details, but there was... I remember some of it. There was a transmission doing a thing called hunting. It was hunting between gears. Third gear, fourth gear. Third gear, fourth gear. But it was just kind of random, like in between third and fourth. And if you look at the options, there were things like slipping clutch, low fluid level, high fluid level, these random different things. And then there was an intermittent connection at the engine coolant temperature sensor. And you're like, engine coolant temperature ain't got nothing to do with it. Are you sure? And the reason that I would select that one is because an intermittent connection might go negative 40, 180, negative 40, 180. Does that sound like it's correlating third, fourth, right? So just remember, some of this engine performance stuff will control how the transmission shifts. Remember the engine state of tune? Like, this is kind of a continuation of the engine state of tune. And then here's where it's typically located, near the thermostat probably. All right, and it talks a lot about all the same stuff. Everything this is going to say is going to be all related to diagnosing a thermistor and the effects that it can have. Cool? Okay, now let's talk about pressure switches. They could be a couple types, and we'll talk about the couple different types. Maybe they're going to be like simple switches, that's on or off. If there's no hydraulic pressure, it's open. If there is hydraulic pressure, it's closed, right? Pretty basic. There's quite a bit we could do with those. If we were to put pressure switches on each of the hydraulic circuits, that'll tell us when the clutches are applying, right? There's a lot of feedback we can do, especially with the torque converter. But there could also be other ones. So this happens to be a line pressure sensor, but I want to break down the difference. How many wires on this one, can you tell? Switches don't need 3 wires. Okay, that's the giveaway. If you got a switch, how many wires do you think? All right, so we go something like this. TCM, remember, like kind of like a box like this. And it might do even 12 or 5 volts. Let's say 12 in this case. And then it goes through. It probably won't even do a resistor. It'll probably just go straight like this and then come out and then this and then this. And then it might even be grounded to the body or to the chassis. And then it'll do like a little sense wire right here. And it could be 5 volts, by the way. Whatever the reference voltage is. In the current state, what should be on the sense wire? Huh? I made it a 12, so let me zoom in for you. It shouldn't have dropped 7 volts to get to the sense, right? So if I made it a 12 volt reference, what should there be at sense? 12, right? Because 12 is going to go all the way down to the drawbridge according to SpongeBob law. I'm ready, I'm ready, I'm ready, right? What happens when it closes?
It goes across.
It does. And so what's the voltage at sense? Exactly. So all the computer needs to do is put a sense wire here, and then if this is closed, it drops to 0, and if it's open, it drops to 12. Or it goes up to 12. Or it could be 5, I don't know. Matter of fact, it could really use any voltage it wants. When the switch is closed and it goes straight to ground, it's going to pull it to ground. That's just basically like a grounding switch. Cool? So that would be a pressure switch. Now, if you wanted a pressure sensor, I'm going to have to draw this a bit bigger. I'll show you why it's 3 wires. We're going to go with a TCM. I'll draw it small here, and then the box is going to have to be larger. And we're going to do something like a 5 volt reference going down on this wire. And then this switch, we're going to have, it's going to be kind of hard to draw this. It's going to be something like this and like this. And then that's a variable resistor, potentiometer type. And then this side would be a ground. And this doesn't generally ground a chassis. This actually grounds inside a bus in the ECM. Okay, so 5 volts goes down, ground comes back. There's a 3rd wire. That 3rd wire, we're going to make green. We're going to make that the sense wire. Or like the signal. We'll call it signal, okay? If you have, it could go either way, okay? But let's just say, if you have 0.5 volts, that's going to be maybe, let's do 0 psi. If you have 4.5 volts, that's going to be, let's say, like 250 psi. If you have 2.5 volts, what do you think that's going to be? Exactly, 125. All right, so depending on the actual pressure applied to this diaphragm right here and the exact circuitry inside there with like some sort of zirconia or whatever, I don't know, some semiconductor material, that part's not really what I could teach you, mainly because that never helped me fix any cars. But understanding this, you fix a my car, right? So if this is a 0.5 volts, I know it's 0 psi. If this is a 4.5 volts, I know it's 250. If I get in the vehicle and it has some sort of DTC set and I look on live data and the live data says, let's go with 0 volts, when should it ever have 0 volts? Exactly. So remember, they're leaving these windows. 0 volts is no good and 5 volts is no good. How would we get a 0 volts? Well, let's break it down. If we lost our 5 volts, there would be 0 right here. You understand? So we could have like a 5 volt bus that's down inside the ECU, or that would be a 0 volt reading, or that would be a 0 volt reading, right? So if you have 0 volts and you should have a minimum of 0.5, the way that we're going to go about this diagnosis is we're going to literally verify our 5 volts. So I'm going to take my meter right now. In fact, I'll go ahead and I'll use my meter clamp stuff. I'm going to say, well, let me hook this to ground. Click. And let me hook this to this. What should my meter say? Should read 5 volts. Yeah, that's exactly right. And if it does, well, I actually could do it down here too. If it reads 5 volts and I have the ground on the actual ground of the sensor, then that means my 5 volts and my ground is good. Up here and down here, you might consider measuring both. It's more important to have this one here and probably this one here. But let's just say I got 0 volts. What's wrong? Could be this, right? Could be an open right there. Wouldn't that get 0? All right, let me trip you out then. What if it was this? What would that read? That would also read 0. You believe me? Try it sometime. Hang this on your red battery terminal and hang this one in thin air. Firmly planted in thin air. It'll read 0 volts. It doesn't mean that the positive doesn't have voltage. This measures voltage difference, right? This is voltage differential. So if it's reading 0 volts, then you'd be like, okay, hold up. Let me put this one on ground to the battery. Clink. Oh, it reads 5. That means 5 volts is good. Then you'd actually move this one over and you put this one on the positive of the battery. Clink. And that reads 0 volts. And you'd be like, oh, okay. No, it's right. You can determine, is it on the 5 volt reference side or is it on the ground side? Cool. Not that hard to diagnose, right? But let's just say you got 5 volts and you got ground, you're good. But let's say that the scan tool still reads 0 volts. How could that happen? Would you agree? Right? If you got 5 volts in and 0 volts out, but you have an open on this signal wire, that would cause you to get the 0 volt reference. Cool? What's this repair entail? What would you say? Wire repair, right? Not a big deal. However, to really diagnose it, right, make sure you got 5 volts in ground, and then you probably leave this one on ground and come over here and be like, all right, what do I have? Maybe right here you have 2.5. Maybe right here you have 0. Then you'd know it's the wire, right? What if you were to go right here and you had 0? What wrong? Remember, the sensor gets 5 volts and ground, and depending on its position, it will vary between a 0.5 volt and 4.5 volts coming from the sensor going towards the ECU. So if I have this on ground and I have this making 0 volts, the problem is the sensor itself. Correct. Then you diagnose the sensor, you replace the sensor, you'll hook it up. But if you had 2.5 volts coming out and that 2.5 volts was not making it to the ECU, that's a wire repair. Now in the very unlikely situation that you have this on ground and this one has 2.5 volts going into the ECU, you know what the problem is? It's an actual open in the printed circuit board of the ECU. If you get to that point, stop. Recheck yourself. Recheck your meter. Maybe go to lunch and come back. Maybe talk to the foreman. Because if you are like me when I was brand new, I did quite a few diagnoses. And like if you do step, most of the time all those steps end at replace the ECU. You basically rush through and you get to the end, it says replace the ECU. It may very well be, but it may very, very well not be. And that's expensive. And there's more than one occasion where I had to explain, I diagnosed it as an ECU and I replaced the ECU and it didn't fix it. Make sense? And then next thing you know, I find out I missed something, I overlooked something, etc. Make sense? Okay, so slow your roll. Now with that, that's how you're going to diagnose those pressure sensors. Again, you're essentially diagnosing it like a potentiometer. If you know how to do throttle position sensor, that's how you're going to do those. Generally, a lot of the position sensors. Cool. Same with a line pressure sensor. We'll have a line pressure sensor, and all that's going to do is it's going to do the same pressure transducer, 5 volts, 0 volts, signal voltage, except that sensor will be where the line pressure is. This one would be a clutch pressure sensor. These are like kind of my favorite because remember when we're saying if you wanted to apply C1 clutch and then you wanted to know if C1 clutch was actually having a hydraulic leak, this is a clutch pressure sensor. So if whatever is applying C1 clutch has one of those, you can really fine tune if it's like a hydraulic leak or a slipping clutch. Cool? So the more of those, the better. In fact, generally speaking, the more temperature sensors, the better. Or pressure sensors. Like the U660 has them. Here they are. It's got pressure sensor for SL1 circuit, SL2 circuit, and SLU circuit. And so we can really diagnose those. It doesn't have it for a lot of the B circuits though. For those, if you have a B, like B1 brake is slipping, it's going to be pretty tough to tell if it's a B1 brake that's actually worn or if it's a B1 brake that's got a fluid leak internally. That's going to be a tough diagnosis because you don't have the pressure sensor. Open it up, or at least in your case, in Toyota Land, make sure it's not any of the externals before you sell it. You don't want to be sending me a message like this message I got yesterday about it's the third transmission, it still does the same thing, what should we do now? Don't. If you took my class, don't. Just don't. I'll be like, I don't know that guy. Depart from me. Okay? You're allowed to make mistakes though, but don't make that. Don't do 3. Maybe 1 because you messed up and have a good reason, but not like, oh, I thought it was another bad transmission. Like, seriously? That didn't even make sense. Okay, now talking about throttle position. Diagnosis is the same. The reason you'd like to know is because the throttle position is an input to the transmission when it generates line pressure, when it controls shift timing. Remember, we had the throttle pressure and the governor pressure, right? But those are gone. We replaced the throttle pressure with the throttle position sensor voltage, which we put into like a table, and we use logic to determine when the shift would be. Here's how you test one with a scan tool. If you were to go into the scan tool and graph the voltage and then apply the pedal, right? Half a volt, apply, wide open, release, 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 right? So that's basically like this. See my hand, the marker will be the throttle. Here you go, ready? That's it. They call this a throttle sweep. It's easy. What did it do? It went from about a 0.5 volt to about a 4.5 volts and back down. Because remember, it's just like that potentiometer circuit I showed you. It gets 5 volts, it gets ground, and it varies it between a 0.5 and a 4.5 depending on its position. This would be a 0.5 volt, and this would be 4.5 volts, right? 0% throttle is a 0.5 volt. 100% throttle is a 4.5 volts. Cool? So it should literally scale up and down. It actually probably might even not be this round. It might be just literally if you can move really smooth. However, what the heck is that? We went up and up and up, and this is a thing. On throttle position sensors, especially the old one, we'd have carbon brushes wiping across it, and then it would get to a little worn out part, and that part would have like no resistance. It would be like worn away. And so we'd have increasing resistance, more resistance, which becomes, or it might even be the other way. Higher voltage, because less resistance, but then it drops off because there's no contact right there. And then it spikes right back up. So it didn't go gradually down and up, it just fell off. And look, it fell off at 3.5 volts, both during apply and during release. That's a notorious open sensor grid on the sensor itself. To be really honest with you, I wouldn't even check this for 5 volts and ground. I'd just be like, oh, yeah, I've seen that before. If it's a 5 volt reference problem, it doesn't consistently drop off in a certain position on the throttle. Make sense? The certain position on the throttle is a thing wiping across the carbon coated surface. Make sense? So there's one area of the sensor that's scratched away or something. Cool? Roberto, go ahead. Please hold. In fact, let me see. Yeah, I didn't put one exactly like that, but this will mostly work. Cool. So look, and this is skipping ahead a bit, but let's just say this is one throttle position sensor right here, okay? Just this side. This resistor is varying, right? So down here, a little resistance, more, right? Less. But what if right here, there's a problem? It's like more, 0, more, maximum. See? So if there's a problem in that particular spot, it'll be a problem at that throttle percentage every time. And that one was 3.5 volts. Remember that? So let's just say this is a 0.5, a 1, 1.5, 2, 2.5. Let's say this one's at 2.5, 3, 3.5, 4, 4.5. If every time you get to 2.5 volts, it drops to 0, it's literally this resistor grid in here. See what I'm saying now? That type of question has been on the ASE periodically. That could also be on A8, by the way, and even L1, but L1 usually give you something harder than that. All right, so back to where we were. So newer cars, they don't have that typical TPS being throttle position sensor. So the old ones had a TPS that was like really basic, like this. Those were easy to diagnose. The newer ones look like this. It's electronic throttle. We're going to come back to the electronic throttle because we got a special page on that one. They have another sensor though that's an input. This is the accelerator pedal position sensor. So like a lot of times on live data it'll say like APP or APPS. You ever seen that? That's a different one. The throttle position is your actual throttle plate. The accelerator pedal is your literal pedal sensor. So those aren't always the same. If you mash wide open throttle, yeah, this might read 4.5 volts, but your throttle may not open that quickly or your throttle may not do exactly what you want. So they can both be inputs. How do you diagnose this? Same as the throttle position. But you have to, if it says accelerator pedal, you need to be under the dash, not outside. That's a different sensor. The way you test it's the same. And then here, this one's kind of cool. ETCSI in the original version actually had it didn't have the sensor under the dash. It had a cable going to here, and then the sensor was like built into one side of the throttle body, and then the motor was built into the other side. So the actual throttle position and the APP would be sometimes combined, but this is a little bit more like the drive-by-wire type we're talking about. So you got your accelerator pedal position. That is an input to the ECM. The ECM is going to actually control the throttle motor and make it move. And then the throttle position sensor itself is going to measure that actual throttle plate, the throttle valve position. So you got a lot of times a redundant throttle and a redundant accelerator pedal position sensor. That's right here. You have two sensors in one housing and they have to agree. All right, so this is where you get into people saying like, I don't want electronics, I want a cable, electronics aren't safe. You mean to tell me that if that sensor malfunctions, it'll have my engine accelerating and my foot's not even on the, you guys remember I told you about the Priuses that would self-accelerate and all that stuff? I'm gonna tell you why I'm not a believer in that. Real simple. Let's just go with 50% throttle right here. Let's make this one a 2.5 volts, and this one is a 3.5 volts. In fact, to make it more clear, 2.5 there, 3.5 here. So if you're at actual 50%, your VPA1 would need to be 2.5 volts. Your VPA2 would need to be 3.5 volts. What do you think happens if they disagree? Let's just say this one's at 2.5 and that one's at 3.0. Boom, the throttle goes to almost closed and you can barely drive the car. It goes to limp home mode. You're done. Boop. We had so many problems with this on Kia vehicles. There was actually a recall to replace the throttle position sensor, which had yet other redundant sensors. But then on some of them, it wouldn't fix it, and you'd actually replace the accelerator pedal, right? So there's two sensors in one. If they don't agree perfectly, the default is no throttle. The default is never wide open throttle, ever, ever. So let's just say you had an issue with this one, and this one dropped off to 0. That's it. You're in limp home mode. The car will barely drive. Let's say you had this one. This line became slightly askew. Boom, the car will barely drive. They made it so safe that those two sensors, which have their own wires, even though they're in the same housing, they have to agree like nearly perfectly. Okay? So when the customers were saying, yeah, it's computer controlled and it just accelerated itself, it's like, I don't think so. You know what probably happened? Doubled up floor mats, pushed the pedal down, Floor mat, you could actually force it past the first floor mat and it would get stuck coming up. You want to know how I know? Because I had it happen. And I wasn't even at the Toyota dealer at the time. I was at a Pontiac dealer. It was all over the news and people were freaking out. And I specifically remember, you could always fact check me. You're more than welcome to. 80% of the time, I'm telling you 100% of the truth. You understand? 100%. Pontiac Torrent, which is basically like an Equinox, came in. The customer said the car accelerates on its own. I'm like, yeah, hilarious. Like, I'm watching the news, whatever. Let me go. First, your job, verify the concern. So I go to verify the concern. I punch the throttle, and it was scary. The throttle totally stuck. It was just going nuts. But in my mind, I'm like, well, there's got to be something mechanically wrong. So you know what my first step was? What would your first step be?
Press the brake.
You could, and this is where Toyota had a little bit of, there was a little dumb here. If you press the brake, you know that the ECM could see that you pressed the brake, but it would still let your throttle go. Okay, they reprogrammed that. That shouldn't have been necessary, but they're like, all right, you know what? We're going to make it so if you press the brake, it automatically kills the throttle. That was a software update. This Torrent didn't have that either, by the way.
If you just hold down the brake and not pump it, for most cars, it will stop.
You could try superheat the brakes. Anybody got any other idea related to transmissions that would stop the vehicle? You could try to throw it in park, but at a minimum, slap it in neutral. The car can't run away if it's in neutral. So that's what I did. Just bang, put it in neutral, and the thing's like, and I look down there, I'm like, oh. I pull the floor mat back, and the throttle goes whack. The pedal goes wham. I'm like, wow, this is a legitimate complaint. I could hardly believe it. But thinking about it, what is the likeliness of this thing reading 2.5 and this thing reading 3.5 randomly? Where did those voltages come from? They have to correlate perfectly. I'm thinking in my mind, there's no way there's an electrical fault. I immediately look, is this pedal stuck? And by the way, I could kind of feel you know when you let off the pedal and the pedal doesn't push back on your foot? Like, you could feel it. So I was like, the pedal stuck. Neutral, bang, pull it back. Got back. They had the regular floor mat, right? The carpet, then the regular padded floor mat. Then they put the WeatherTech on top of it. And if you pushed hard enough, it would nip past the edge of the WeatherTech and be stuck under there. So I just had to yank the WeatherTech back. And then it was like, it's all good. Told them, hey, we're not really part of this whole recall and stuff, but you can't be, you can't be shoving a bunch of stuff that's going to make your gas pedal stick. That's not the fault of the manufacturer. Like, stop shoving junk down there. It's really no different than if you had a bowling ball on your lap and you hit the brakes and the bowling ball went and smashed the throttle to the floor and the car accelerated. Whose fault is that? You can't, the bowling ball's fault. Yep, definitely. Matter of fact, I'd probably sue the bowling ball manufacturer. It didn't say on there, don't drive around with this on your lap. Matter of fact, if the hot coffee spilled on my lap, I'm suing Dunkin' Donuts for not putting "this is hot" on the lid. True lawsuit. You see, that's how you get rich. Yeah, definitely don't get skills, just get a lawyer. Okay, but makes sense? This is pretty safe. So if you had to troubleshoot this, it's the same type of thing, but you're going to be graphing this. You can graph these voltages on the scan tool. The details of that you'll learn in engine performance. Now, similarly, in the actual throttle body, we have two sensors. And these ones, they don't go the same direction. They actually go opposite. So if you're closed throttle, one will be reading 4.5 and one will be reading 4.5. One will be reading 4.5 and one will be reading 0.5. At half, they'll both be reading 2.5. At wide open, they'll be reading 0.5 and 4.5. Makes sense? So they're like equal but opposite. So there's double redundant sensors on the pedal and there's double redundant sensors on the throttle. If these two disagree with each other, kill the throttle. If these two disagree with each other, kill the throttle. If this disagrees with this, kill the throttle. If there's any sort of variation at all, kill the throttle. Kind of frustrating. But all these are inputs to the transmission. Make sense? The chances of it being an electrical fault making it accelerate on its own, I just don't think so. The chances of this causing a transmission issue, yeah, maybe, but that's why we're checking codes. If you have some sort of throttle position correlation, you're fixing that. Do not start trying to put a transmission in the vehicle. Don't. You got to fix all the throttle stuff. Remember that procedure? The engine has to be in a proper state of tune. If these are malfunctioning, it's not in a proper state of tune. And then they even have more basic ones where, like, if the throttle's closed, it'll connect an additional switch just to say the throttle's closed. That's important a lot of times for like torque converter lockup. If your throttle's totally closed, we don't want the torque converter lockup. Cool. And then with map sensors, this is the same exact thing as a transmission temperature, transmission fluid pressure. It's a 5 volt, a diaphragm, right? It's 3 wires, 5 volts, ground, and a signal circuit, and it's on a pressure transducer, like same. Why is this in transmissions? It's a map sensor. What the heck we want to know about that for? Yeah, exactly, but why? Old transmissions, what they used to use sometimes. There's a term for it. A pressure, it was a vacuum modulator. They'd say like modulator pressure versus governor pressure. This is the same as actually a modulator. It's just electronic and not vacuum hose, vacuum line. Make sense? So this measures vacuum, but we make it into a voltage. So it's another input for engine load. You guys know at wide open throttle, you should have 0 inches of mercury, right? So this is just going to confirm engine load in addition to the throttle, and we can combine all those, and the mass airflow sensors come, and we can get a really good indication of what's going on with that engine. See, like math. Cool. So problems with any of those sensors can cause problems with the transmission because they're all inputs to the transmission control module. Get it? So you really do have to understand some engine performance to even be able to understand transmissions in a way. Cool. So mass airflow, it measures the mass, in other words, like the weight of the air. It does it in a few different ways. There's like 3 or 4 different types. We won't go in great detail, but just understand when the air flows past the math, it measures it. If you have like a crack right here, actually a crack right there wouldn't be a bad deal because it goes this way. But if you have a crack right here, air is sneaking in, it's not being measured. That's going to actually cause you some engine performance issues. And that would give your transmission control module a false understanding of how much air is coming in and therefore have some effect on how it shifts. All this needs to be in good condition before you start condemning a transmission. Cool? All right, and then this talks about the test. The testing is a little bit too in detail to go nuts over, but generally we can use the scan tool data and look at like how many grams per second at idle, and then make sure it goes up, and there's some specs. Cool. And then another one, the brake on off switch, you can see this one's up on the pedal, and here's what it actually looks like. So if we were to do 12 volts to the switch, and the switch was open, 12 volts dies right there, it doesn't go anywhere. What's the PCM see right now? 0, right? If we step on the brakes, 12 volts goes to the brake lights and they go, woo, like that. Am I right? What's the PCM see now? Exactly, yeah. So the transmission control module, or the PCM, whatever, needs to know when your brakes are applied, and that's how it does it. It'll just pull an extra line off of the brake lights, and it can know. They can do it in several different ways, but they're pretty simple. This is especially important with TCC release. So you remember I told you guys about a Trailblazer and it was stalling and stuff like that. When you hit the brakes, you don't want your torque converter locked up. If you hit your brakes and you come to a stop and your torque converter is still engaged, the engine dies. As soon as you hit the brakes, you want the torque converter to disconnect. You don't want them locked up 1-to-1 anymore. And then more like from an ECM standpoint, you can just see it's an input here, right there. That's the electronically controlled transmission ECU. Here's the stoplight switch. There can be an adjustment right there. If you had a vehicle and it had a problem with cruise control in op, brake lights having a problem, and a transmission issue, that's going to be some with that brake light switch. All those systems rely on that, okay? And it could even be just like a loose adjustment. Loose adjustment, a lot of times if this thing's backed off, it'll actually show it on all the time. And if it's so far down, you'll actually have to push the brakes really low. And so the customer may just be tapping the brakes and it's not actually closing the circuit. So consider the adjustment a little bit too. Cool. You guys know how you test that, right? You could test it a couple different ways. If you look at it right here, you could just put your, if you want to go old school, you could actually use a test light right here. But let's just say we use your meter. With the brake pedal depressed, you should get 12 volts here. With the brake pedal released, what should you get here?
0.
Exactly. 0 volts released, 12 volts when applied. So it's really easy to test. You could also just look at the scan tool and find brake pedal, applied and released, and you can just watch how it changes and get an idea if it's in the right area. You'll also get some sometimes that are like adjusted right on the edge where like if you just lightly just graze the brake pedal, it'll show them applied, and that could give you some of these weird torque converter concerns. Cool, so there's an adjustment for that. Manual lever, I think you guys know that's your shift cable. Here we got a range switch. Kenny and Marty, as far as I know, were the only ones to perform that adjustment in the in-car service. We're just, you see, there's so many jobs to do. I feel for you. But that one's got an adjustment procedure. To really understand it, you could do, how long you think they could do it? Half hour? I think you could do it in a half an hour. So add that to your to-do list. The adjustment's pretty simple. If the adjustment's off, your ECM, your TCM uses this. If you put the transmission in reverse, yes, you've moved the manual valve to reverse. But this sensor needs to know that you're in reverse. If you're not, it's not going to send the right signal to the TCM. You may not have backup lights either, but you know, the TCM needs that information too. So there is a little bit of an adjustment on here. And if we had an internal problem in there, a lot of times you get a DTC, but you also might get some funny different symptoms, like especially with reverse. It needs to know that you're in reverse when it actually applies the correct shift solenoid for reverse to work. Cool. And then overdrive switch. Who is not totally sure what overdrive means? It's okay, because I've heard quite a few different songs talking about put it in overdrive. I heard one, put the engine in overdrive. The engine don't go in overdrive. And additionally, if you did put the transmission in overdrive, that wouldn't be for more power. Like overdrive, you remember when we talk about the planetary gear set? Underdrive gives you more torque. What's overdrive give you? More speed with less torque. So like, now do you understand what overdrive is? If you're trying to save gas, of course, overdrive. If you're towing a trailer, you may not want overdrive, actually, because overdrive is gonna drop your engine RPMs, and actually it makes it really hard for the engine to turn because the engine's turning slow and the wheels are turning fast. So it's kind of like reverse, right? It's not generating more torque, it's generating more speed and making less torque. So there's some instances where you may want overdrive off, mostly if you're towing. So that's an input. You can see this one's on the end of the shifter stock. So if you see stuff about overdrive, you know, just know overdrive is gonna most likely disable the highest gear. So if it's a 4-speed, it's only gonna go to 3rd. If it's a 6-speed, it's only gonna go to 5th. Cool? Just disables the highest gear. Cool, and then that's, on this design, ends up being an input to the ECM. So if the ECM gets an overdrive off switch, it'll most likely turn on a light, OD off, and it won't shift into 4th. So if the customer is complaining it won't shift into 4th, and you have OD off on it illuminated, you need to really diagnose what's up with the overdrive switch circuit. Maybe the overdrive switch circuit is shorted or something. Cool? And then manual shift buttons are pretty cool. So where overdrive off is good, this can do everything overdrive off can do and better. So like if you want to manually shift, you can manually shift. If you wanted to, let's say you're towing the trailer, you can put on tow haul mode, by the way. I don't think I put that on here. Tow haul mode a lot of times will delay your shift points higher, increase your line pressure. Why do you want that? Towing a big heavy trailer. What you got in the trailer, Roberto? What kind? Integra in there. All right. Are you towing the Integra with another Integra?
Yeah.
Put it in tow haul mode. Oh, you're towing 2 Integras with 1 Integra and a trailer. All right. So let's say you get the Tundra and you want to haul another Toyota. You could put it in tow haul mode, increase the line pressure so your clutches don't slip, increase the shift, delay the shift timing so that way you're keeping the engine RPMs up and it's going to pull better. Cool? But also, let's say you crest the hill and you start to go down. Let's say you hauled those things up the Cajon Pass and you went to whatever the place is everybody drifts up in the high desert. I can't even think of the name. Apple Valley. Yeah, so there you go, goofing around at Apple Valley with a rear-wheel drive car. And then you get ready to come down the Cajon Pass and you're like, okay, I got a car behind me. I can ride my brakes and smolder and warp the rotors. Or I can manually downshift it, right? So you can use some engine braking. So a lot of this is helpful, especially with towing. That's why you'd have these manual switches. But you could also have it more for sport too. You can pull this one over. And this is not the right way for me, if you ask me my opinion. When you pull this over here, how do you upshift? Can you see? Yeah, if you can see that, this is plus and this is minus. So when you upshift, you're like, see, to me, when I think of my upshift, I always think about that really fast 1-2 shift, which is like this. I would do it like this: first, second, third, right? And then when I'm slowing down, like boom, boom. So I don't know. It's all backwards to me. They didn't ask me, so I'm just letting you know. You understand what this is? This is just an input to the ECM or to the TCM, let's say. If you're driving down the whatever road, Valley View, and you yank the thing over here to manual, the TCM's now like, okay, stop shifting automatically. What do I do next? And you're like, first. And it's like, really what you're doing is requesting first. And it's going to say, let me look at my speed, let me look at my RPM, let me look at my info, and then it's going to be like, no, I'm not doing it. You can't make me. And then you'd be like, first. And it's like, no, until your first request makes sense, and then it'll do it. Makes sense? So this is like more of a request more so than a command. You can say please, you can talk nice to it if you want, but ultimately your TCM will no longer command upshifts. It may not command downshifts either, but it may also stop you from downshifting it manually. But as soon as you pull that over and you're in first, it's just first, and then you can upshift it, and you can try to make people think you have a manual if you want, but that becomes an input. That both of these switches are kind of similar, so I'm going to lump them. When we're pressing an overdrive switch, again, that's going to become an input to the ECU. So like right here, you can see pretty well. Your ECM, maybe this one's for overdrive. Do you see how this switch, if it had 12 volts, when you close the switch, it'll drop that to 0 volts, right? So this is all just switch inputs. It puts out a reference voltage, and when the reference voltage drops to 0, that's how it knows that switch closed. Same with an upshift, same with a downshift, same with all that. They all work really the same. So if you wanted to know if this overdrive switch worked, how would you test it? You could get a power probe, but that was not where I would go first. Exactly. You go live data, then you go overdrive switch, press it, and it goes on, off, or depressed, released, depressed, released, depressed, released, right? This is a quick way to check all those inputs. If you want to know if that upshift and downshift works, go live data and just look like up, 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 down, down, down. Yeah, it works. Make sense? Checking all these inputs is going to be really the same. Live data is quick. Now, if it doesn't work, then you're going to have to actually start measuring. Does it have 12 volts here? Is the 12 volts getting to here? Is the ground getting to the switch? And then is there continuity when this is depressed? Make sense? But like initially, it's just scan tool. Cool? And then if we look at the shift lock, who thinks they know what the heck shift lock is? Shift lock.
reverse.
Kind of. So if you jump in the car and you go to move the shifter and it won't work, the shifter won't move, what do you think you might have to do? That overrides this. So when you pull off the little cover and you push a screwdriver down there and you manually move it, that's because there's something wrong with this shift lock. So what the shift lock looks for is key on, brake pedal depressed, then it'll allow you to shift, right? So like in a GM, they called it BTSI, brake transmission shift interlock. This is just locking you in park until you do key on and press the brake pedal. That's it, right? Right here. This solenoid will block you from pressing that button. You can override it with your screwdriver and that little access panel, but if it gets the right ignition switch and the stoplight switch, then it will actually activate this, and you can hear a click. You ever notice when you step on the brake pedal, it goes click? This is the faint little thump down there. That's the solenoid releasing that. So that's generally not real transmission related, but it's still kind of related. If the customer comes in and they say, my transmission won't shift out of park, they may think that it's a transmission issue. That's really like more of just an electrical issue. But sure, we'll take it. We'll take all that work. Similar with the neutral safety. So we covered this already in the range switch, but with the neutral safety switch, that a lot of times will come in as a no crank, no start, but we may very well be looking at the transmission, looking at this adjustment, and as you can see, park and neutral are needed to allow that actual starter. Cool? But if you also look right here, there's a whole bunch of switches. Cool? And the ECU needs to get a reference of each one of those. So if you look at this one, let's say we send B plus, you see this? B plus is red. Right now, which terminal is going to get 12 volts? Just P, so the actual ECU doesn't get anything. What if I were to, and you're right, and B too. What if I were to go and put it in reverse? Which one would get it? Can you see it? The R at the ECU. Make sense? So that's how the TCM knows where your shifter position is. What if you pull it into neutral? Oh yeah, but it doesn't look like it really goes to the transmission ECU because it doesn't really need that. Like if it gets nothing, it knows you're in park or neutral. What about when we actually pull it down into drive? That's down here. I pointed the wrong one. Drive. That's where it's going to get it up there. Make sense? I can't quite reach that. Don't make fun of me. Cool. So your ECU needs this as an input. This tells the ECU what gear position your actual shifter's in. Who remembers where that switch is? Yeah, it's not at the shifter. Most people go and they start looking at the shifter and they're like, oh, where is it? It's not at the shifter. The shift cable moves way out the transmission. That switch is going to be at the transmission almost every time. Okay? Still do some diagnosis there. And then this also talked about the manual shift mode. Okay? And then you have some like this. So when we're talking about moving it into like low, that's when you're like, here you go, drive, or then 2, and then low down here. This one, reverse, neutral, drive. 3rd is basically like turning overdrive off. 4th in this case is overdrive. On a Honda, they'll actually do this. They'll do like O, D circled, and then D, which is really D, or sometimes they even do like D3. That'll only go to 3rd. Make sense? So this is another way of manually controlling the automatic, at least to some extent. Cool? But that's through the manual valve, not just through electronics. And then, of course, good old column shifters. You guys have used these, right? Park, reverse, neutral, drive. And then sometimes they'll have like sport mode with ups and downs. Very cool. Now, why do you think they put this junk on there? Do you want it in your Sienna? This one happens to be a Tundra. You don't want a Sienna?
Did I say this on?
LE? Oh yeah, they are sometimes column shifters, that's true. All right, well here's why. Let's just say you just put it in drive and that was it, and then you went up this hill. Here you are. You're in fifth, you hit the hill, it's like, okay, fourth, then you hit fifth, and it gets steep and you go third, then you go fifth, then you go fourth, and then you're kind of like fifth cruising, but you're braking, right? Could we do better? If we have with control, maybe you're in fifth, you go into fourth, but you're like, you know what? I already know it's going to try to upshift right here because it flattens out. I'm just going to pull that sucker into fourth and just maintain fourth the whole way. Why is that better? Or is it better?
It's better for more torque.
It's better for more torque, but remember, every time a transmission shifts, it lets go of a gear and it grabs another gear. So it lets go of, let's say, the ring gear, and then it has to grab a sun gear. Each time that happens, it wears a little bit on the clutch. Can you follow the logic? You don't really want that transmission third, fourth, fifth, fourth, fourth, fifth, fifth, fourth, 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 third. It's like, just chill out. I'm going to pull the sucker into fourth, and I'm going to ride fourth the whole way. I will need third there, but then I'm going to pull it into fourth, and I'm going to ride fourth, where I would be fifth, and then it'd be back to fourth. And then in fifth right here, you're coasting a lot. If I pull it into fourth, I'm saving all my brake application too. So some of the newer transmissions do a better job with this, but especially like some of the older stuff, like they'll be shifting all over the place. And it'd actually be nicer to do this. But see, your computer has no way to know that a downhill's coming up. You do, because you know where you're going. So it's okay to pull it into manual and you do your own little bit of shifts. Kind of make sense? It's actually be better for your transmission if you did this lower one. Fifth, fourth, third, fourth, third, fourth, fifth is better than fifth, fourth, fifth, third, fifth, fourth, fifth. Make sense? And then third, fourth, fifth. Cool? That's just kind of one of the little bonuses for why those manual things are there and stuff. Now, do we try to educate the customers on this? No, we don't. But some people are enthusiasts. Some people drove manuals or drive manuals, and they'll be like, I'm going to manually shift this because I know how it feels better and stuff, and they might be right. You like it, Roberto? You know. All right, now we're into outputs. All right, so you covered all the inputs. Remember, all the inputs are like the sensors to the system. They're all giving information to the TCM. Then the TCM is going to look at its logic. Now the TCM is going to control outputs, okay? So we're into outputs. The outputs are the shift solenoids. We're going to call it, as you can see, an electromagnetic type of valve that's either open or closed. Basic right there. If the valve is off, generally speaking, it's closed. How would you open it? How would you open it? Give it 12 volts and give it ground. And then it's open. That's for most of them. Some of them are actually normally open and we have to power them to close them, but that'd be a little bit less normal. Like pressure control maybe. All right. So now what do they mean by electromagnetic? That means it gets 12 volts and ground or some electricity to move a magnet that opens or closes an actual physical valve. So you have pressure going to a valve and the valve is closed. How do you allow the pressure? Give it 12 volts in ground and it will magnetically move and unseat a pintle and the fluid will flow. Okay, so just so everybody's clear. These are electronic devices to control hydraulic pressure, basically. Now they can directly control line pressure to an application device. So if we wanted, here's your basic gear set. If you have an input shaft right here, and you want this input shaft to be connected to this sun gear, you can be like, hey, apply C1. How? Shift solenoid S1 active will pump up the piston for C1 and grab it. Cool? So now I can control this grabby clutch using a solenoid. C1, grab. C1, release. C1, grab. C1, release. It's as simple as giving 12 volts or giving ground. Some solenoids get 12 volts all the time and we ground control them. Other ones are grounded all the time and we voltage control them. Either way, kind of same thing. Okay, and then 4-speed automatics, back in the day, used just 2 shift solenoids. That's it. Shift solenoid 1, shift solenoid 2. It's so simple. And the ASE was based on 4 speeds for a long time, but it's not. Okay, those days are gone. Newer transmissions use many more. All of the gears needed can be hydraulically applied by turning different solenoids on and off. So you want 1st, 2nd, 3rd, 4th, 5th, 6th, 7th, 8th, 9th, and 10th. Whatever, 11th, maybe. Whatever gear you want, it's going to be a combination of the different solenoids. This one on, this one on, this one off, this one on, this one off, this one on. Make sense? And there can be quite a few of them in there. And then, like on a 4-speed, this is what was kind of interesting. This is a half truth right here. This was true, but it's no longer true. On a 4-speed, off, shift solenoid 1 off and shift solenoid 2 off was always 3rd. And that was on purpose. So if you look at this, right, this is a basic 4-speed. It's to illustrate a point. You still may work on some 4 speeds, but that's not the norm. How do we make first gear? You guys tell me. On, on. If you want first gear, I'll give you the formula. Shift solenoid 1 on, shift solenoid 2 on. Can you do that? How do you make second gear? Off, on. This is pretty hard. If you have off, on, you have second gear. How do you make third? Off, off. Cool. How do you make fourth? On, off. All right, now I'm going to give you a lesson. And again, a lot of times the purpose of the story is just to help illustrate and make it very practical for you. So I have a history with Jeeps and transmission problems. I really do. So I got a call, same guy whose Jeep I fixed earlier, except now it was like we're a couple years into dating. He gained some respect. Now he's thinking like, oh, this guy can fix anything. You got to understand the pressure of that. Having the pressure of you can fix anything, even though I'm thinking like, I don't know. That's how I lost my hair. Just the pressure, thinking I can fix everything. Well, I got a call. Hey, my Jeep is having issues. It has no power. And by then he'd kind of figured out, I think it's something with the transmission. I was like, really? It's like brand new. The thing was like a year old with like 10,000 miles or less. So I'm like, okay, if something's 10,000 miles and 1 year old, do you think that the transmission's worn out? But electronics can fail when they're a day old, right? So I'm thinking it's electronic. He called me, so I bring a few tools home, bring some basic electrical stuff. I don't bring tools to drop a valve body, okay? That was when I first started. I was an idiot. I'm just letting you know. Like, I'm not going to do that again, but I'll bring some basic stuff. I'll do some basic diag. I jump in the thing. I check the codes. No communication with the ECU, with the transmission control module. I'm like, all right, that's weird. So I jump in and I put it in drive and I punch the gas. And you know what it does? It sounds like these cars out here that I heard today. Whoa, they barely drive, huh? Well, how would you feel if you're starting off in third gear? Not good, right? Take that mountain bike, that bicycle, that whatever, put it in third. You can make noise, Crunchy. I got the microphone. I'm going to noise cancel all that. We can pedal the bike. You start off in direct drive. That's going to be really hard for your legs. Can you feel the burn just thinking about it? Your legs are going to be like it's going to be tough. Well, that's what happened. I jumped in there and I was like, oh yeah, this thing is definitely not in first gear. And then I thought about it and I'm like, no communication with the TCM and it's acting like it's in a higher gear. What gear do you think it's in? If there's no communication with the TCM, what's it default to and how do you know? Not exactly. But whatever off is what happens if there's an electrical failure. Make sense? If you have a bad TCM, if you disconnect the transmission, it'll default to whatever off is. Make sense? So the engineers designed it like third gear, honestly, it's going to be slow from a start. But could you make it home on the freeway? It wouldn't be very nice though, but you could make it. Could you get up to speed in the city? Eventually. So third's the only choice, right? Third gear can get you where you need to go. It might not be the best, but if it defaulted to first, it'd be great around town, but you could never get home on the freeway. If it defaulted to fourth, it'd be amazing on the freeway, but you may never get up to speed. Make sense? So they've designed it so if you lost power and the solenoids were both off, it'll generally be something like direct drive. On our cars, that's generally fourth. So if you have a major problem with the transmission, like Renee, remember that one you had and you got out there and you drove it and it was like, bah. Then you check and it had no communication with the TCM, or it had something along those lines. I think it had all the shift solenoid code set because actually the TCM was working, but it had no connection to the actual transmission. If there's no electrical connection, all the shift solenoids are off, okay? So I kind of figured that out because by then, like I'm saying, when you graduate, first off, when I worked on the first Jeep, I was still in school. But from the time I graduated school, having learned a lot of the theory, and then I put a couple years in as like a line tech, I knew a little bit more, like a lot more, but there's still a lot I didn't know. So it's kind of like, oh yeah, this is defaulting to third gear, like right off the bat. Cool. So there's a little bit more to the lesson, but do you understand why third gear is off? Do you understand how I could kind of jump into this things in what we call limp home mode, and that's something that comes up a little bit later? Just off is limp home. It'll barely drive. Now think about it for a second, because there's an ASE question concept that I've seen on there. If it was no communication with the TCM and defaulted into direct drive, what do you think you'd check first? Check for codes, but it has no communication. So I like that idea. You're right. That's why I checked for codes, but it said no communication, right? If I'm using one computer to talk remotely to the TCM and it won't communicate with it, what should I do? Fuse is a good idea. I could look to see if the TCM is plugged in. In this case, I found out the TCM gets its power supply from a relay. I literally just back probed the TCM right there in the driveway and said, oh, the TCM's not getting any voltage. And then I back probed it again and I found out the relay's not putting out any voltage. It could be, but it started fine. Yeah. But then I back probed going into the relay. Going into the relay had 12.6. I like that. 12.6 was good, but coming out of the relay, it had 0. What's your diagnosis? The relay. I switched the relays, and guess what? His horn don't work, but his transmission works. I mean, it was that dumb. And literally, so I wrote a little note. This relay was bad. This relay is good, but this relay goes in the horn, and this relay is the TCM. I wrote up a whole explanation, all this stuff, and then I said, yeah, like take it to the dealer and let him know because it's under warranty. I could have got a relay, but it's under warranty, so he should really, have it done through them. You imagine being the tech that pops that fuse box and sees my little scribbly writing on a masking tape and is like, whoa, this guy, I'm gonna flag this hour, diag. But I wanted to get it going. So it makes sense if you have no power, why it's in third, right? No power is default off. Cool. So that was yet another fun time. Of course, he now thinks I'm a genius. I can promise you I'm no genius. I can understand off, and I can also check a relay. That's all I needed to be able to do. Not even that hard. Now about the solenoids. Here's your on-offs. Okay. Here, and by the way, these can have a little filter and a little screen. But basically, if we have this off, there's going to be really no pressure flowing. There's going to be no fluid flow. And then if we end up going on, you can actually see we're going to allow big pressure to flow right here. Now, there may initially be some pressure that's just kind of like over here, just kind of like going in and out, but it's not actually flowing to the passage yet. Kind of makes sense? So depending on the design, it'll block the fluid or it'll allow the fluid is mostly what we need to know. Sometimes they do a little bit more than that, but generally that's it. Now there's one thing you have to understand. Very, very important. I'm gonna draw some stuff. Here we're gonna have 12 volts. Here we're gonna have ground. That goes into a coil, which will draw a different color. Do you understand? 12 volts goes into this coil and it comes out. So if you have a shift solenoid circuit code, that just means it's not dropping the expected voltage. So couldn't you have like an open right here? Wouldn't that set a shift solenoid circuit code? Yeah. How would you diagnose that? I agree. Resistance. So you guys got some vehicles out there that have some shift solenoid codes. I lost, here it is. So you could literally put this thing on resistance, isolate it, right? Disconnect this here and here and measure it. What's the spec? I don't know. Does anybody remember a shift solenoid spec? Let's just say it was 4 to 6 ohms. Cool. Remember I told you I diagnosed shift solenoids once? Well, here's the rest of the story. Now, I went in the valve body, right? I had the pan off and all that. But technically, let's say if I'm right here and it's 4 to 6 ohms, if I get like a 6.2, I'm not worried. If I get like a 5.1, I'm not real worried. I'm sort of like, hey, that's a little low. But you know what? This is very dependent on temperature. So depending if it's hot or cold, like it'll vary. If I do it like this and I get a reading of 10 meg ohms, does that sound normal? No, that's not even close. Now, if I measure it right at the solenoid and I get 10 meg ohms, what's wrong? The solenoid's no good. And that's exactly what happened to me. And I measured 2 of them. I think there might have even been a third, but I think one was for torque converter clutch application. But I measured 2, and 2 of the solenoids were bad. And that was the one I told you. The shift solenoids were like stupid money. Stupid, like $300 a piece. Was nuts. Cool. So it was a really simple diagnosis. Now, does anybody remember what the defect or like what the customer concern was back when I told you that story? Remember or no? Another Jeep, different 96. Put it in drive. First. There was no second. Second never showed up. Except once in a while, it'd be like, bam, second. But then the next time it'd be stuck in first again. Do you see why a shift solenoid would cause that now that we've discussed a little bit about what shift solenoids do? That shift solenoid needs to control the application. So let's go back to that chart. This one's a little bit different, but let's just say, I'm gonna modify it for now. Let's just say it was on, and this one was off, and then it went to on. Actually, on, off, on. Yeah, and this one became on. You can see my green writing, right? How do you make, in my imaginary one, in this Jeep, I don't remember it in that detail, okay, it was a long time ago. But in this imaginary one, how do you make first? On, off, right? Thank you. How do you make second? So what if shift solenoid 2 was bad? What would happen for second? What would happen? First, and then it'd be like, hello, I'm commanding you on, but instead it's like, nah, I don't work, right? So if it's on, off, that's first. If down here it commands on, but this one's broken, that's really like on, off. So that's first. And it's first, and it's first. Make sense? So that solenoid was no good. The symptom exactly, perfectly matched my measurement with my meter. So it was a really easy diagnosis, actually. But that was easy because I was already in the valve body, okay? So if you are trying to do this, remember, we can measure at the valve body, but as you'll see as we get a little bit further, when it's a circuit code, that just means it's an open somewhere. An open here would do it, right? That harness could be inside the transmission, or it could be after the connector, and it could be going up towards the ECU, right? So it could have been a harness outside the vehicle. And that's where you got to get your diagnosis down. Because if you tell me it's a shift solenoid or cell of transmission, and the problem ends up being outside the transmission in the harness, you're fired. I'm going to fire you. The boss might not fire you, because to be honest, if you get to the point where you're showing up to work every day and you can actually fix most of the cars, you're too hard to replace. But I'm still going to fire you. Okay? And that, remember, that was for a shift solenoid circuit code, and you can see what the symptom would probably be. Now, there's other things that could happen, because look, what's this? Filter. So what if this filter was all clogged up with toxic sludge from lack of maintenance? Would it set a shift solenoid circuit code? The circuit code is set because it drops a certain amount of voltage or it doesn't. That's for defects in the windings or the harness. You could have a shift solenoid that is electrically fine, but when it goes on and it tries to flow fluid, it just doesn't flow fluid. So what codes is that going to set? It might not set any codes. It might not shift. It might have funny issues, but it might not set any codes. It could be a little tricky. Renee, go ahead. Okay, ideally, if I could say ideally, I would go over here, and do you remember this shift solenoid over here was the 2-3? And this one was the 1-2? And if you go way back, remember Toyota said SL1 and then it had pressure sensor SL1? You see now, if you had the pressure sensor for shift solenoid linear 1, you could use that sensor to diagnose that the fluid was actually making it there. So if you applied that solenoid, you could look at pressure sensor SL1 and verify that that fluid is making it to the circuit, and therefore you know that that filter is not clogged up and that that solenoid is not only electrically working but mechanically working as well. So if you wanted to know if the shift solenoid was flowing, totally different, difficult diagnosis. Same with the injector, right? You could test an injector electrically pretty easily, but actually to test it for flow, different kind of issue. So got to know that it could be both. Now let's talk about more of an advanced one. So a linear shift solenoid does something different. The linear shift solenoid not only goes on and off, it can actually ramp the pressure up. It can do it at a varying rate. So if you wanted to control not only shifting into second, but you want to like shift into second really fast or really slow, or kind of like firm or soft, these linear solenoids can do all of that. The linear solenoids can really fine tune the shift, especially when you get into that CVI, the clutch volume index. This is the way that, remember we had the 100 thousandths clearance and then the 60? If you put in one that had 60, you could actually have this shift solenoid slowly ramp up. The computer can slowly ramp this up and that'll smooth the shift. Or if you put it in sport mode, it'll say, you know what, ramp it up fast and you get a really firm shift. So these linear, these control not only shift timing, but also quality. When you have this type of solenoid, you have less of a need for those accumulators and things to really dampen it. We still tend to use accumulators, but we can also do a lot of that dampening through precise control of the solenoid, okay? The other thing to remember about these, with the on-off solenoids, that's 12 volts in ground or not. Make sense? With these, we duty cycle these. So if you look at what the transistor does, the battery plus goes to the solenoid. This is going to be the solenoid. It has power all the time. And then this transistor in the ECM is going to actually duty cycle it, right? So if you guys were to see up here, your duty cycle were to look like this. And these are the same. What duty cycle is that? About 50 on, yeah. 50 on, 50 off. And then if you were to want it to be on more, this is ground controlled. So actually down here is on. Up here would be off, on, off, on, right? So this might be like a 90% duty cycle. So if you want to actually test these shift solenoids, you know what you need to get out, right? If you really want to see if they're getting the signal from the ECM, you understand what you have to get out, right? It's going to be picoscope. Now, we talked a lot about the circuit. How do you know if the problem's in the solenoid or the circuit? Well, you can still measure resistance of these solenoids, and that'd probably be the go-to. Resistance is a good measurement. It's sort of like testing something in a static state. If you want to really test it dynamically, though, that's when you'd have to do duty cycle. The duty cycle test would be more like you make sure there's 12 volts here, and then over here, you could actually do like, take your probe for the picoscope and look at your duty cycle, and let's just say right here, your duty cycle was like this. And then reprobe it right here, and if your duty cycle is like this, what's the problem? The duty cycle here good and the duty cycle here bad, you know, that actually I did that backwards. Let me switch that. I forgot which way it was going here. This one flat line, this one getting good duty cycle. Now what's wrong? Yeah, that'd be open circuit, exactly. So that's how, again, you can bust out the picoscope and the picoscope can give you really good info, but ultimately, you're not really trying to diagnose typically like how exact this transistor is working. You're more like, is it a wire? Is it a solenoid? So, you know, you could shoot right for duty cycle on this, but probably what I would do, if I thought it was this wire, couldn't I effectively figure it out like this with my meter? Right? Just put it on resistance, do my 12 volts and do my ground, or do my resistance measurement right here, boom. And if it's an open wire, what do I get on resistance? Oh, well, yeah, exactly. So there's a lot of different ways to do the diagnosis. Now, as for the shift solenoids, what do? This is Toyota specific terms. The ASE stuff will be a little different, full transparency. SLT is line pressure control. I want to make a note on that one right there. On the ASE, they're going to most likely call that one this thing, and we're going to come back to it, okay? So I'm going to put it right here. EPC, electronic pressure control. That controls your line pressure. If your line pressure is high, what are your symptoms? Banging gears, that's right. You guys felt high line pressure. You put the car in reverse and you got whiplash. Poof, broke grandma's neck. Sad story. Okay, so on Toyota, that's SLT. If you look, there's SLN. That's how we control some of the accumulator back pressure. We can fine tune the shift field. We got S1 and S2. Those are on-off solenoids. The SLs, you'll notice, those are duty cycle. The duty cycle, those are the ones that we can control timing and quality. Those are progressive solenoids that they're not on or they're not off. They're kind of like a dimmer, right? So S1 and S2 are simple. SLU is lockup solenoid. That's torque converter clutch. On the ASE, SLU will be like more like TCC. That's it, torque converter clutch. So it has their own terms. And then SLU is always a flex lockup solenoid, whereas like back in the day, it could be SL for lockup, or SLU is on the newer flex lockup. They're all flex lockup now. And then there may be a relay valve, SR. There's SL1, SL2, SL3, SL4. This is a big one. These are shift solenoids, but they're linear, right? So if you get into like an 8 or a 10 speed and you want to have control over 3 or 4 different planetary gear sets, you need more solenoids. But you also want to control exactly how they feel with the clutch volume index and the transition adapt pressure, so they all shift the same. That means you also need to have them be linear, right? The linear solenoids are a lot more money. They're more complicated. They're not on and off. Those are duty cycle controlled and stuff. So like a newer transmission that has all these, definitely going to be more money, definitely going to be more complex. When we look at some of the shift charts for the newer stuff, you'll see it. There's a lot more going on than the good old 4-speed with 2 shift solenoids. Okay, and then S4, sometimes for overdrive, but that was kind of on like the old school transmissions. And then you might even have a couple different lockups, and then there's even one that would modify the 3/4 shifts, but this was really only on one transmission anyway. All right, so here is SLT, and remember what I'm about to tell you has got a lot to do with EPC on the ASE, okay? SLT, you got the pump pumps, it's going to go to a pressure regulator valve. The pressure regulator valve is going to basically get an input, and it's going to get an input from SLT, okay, or EPC. EPC is ultimately controlled by the ECM. So the ECM controlling EPC controls this pressure regulator valve, which controls the whole transmission line pressure. Now here's what's crazy. If you look, the more current you have, the lower your line pressure. Okay, that's critical. The less current you have, the higher line pressure, right? So let's just say, let's make this 0 milliamps. And then let's make this like maybe 1 amp. I don't know exactly how many amps it would be, but if it had 1 amp flowing through it, what would your pressure be? Less, exactly. Whereas if you had 0 amps, what would your pressure be? High. Do you think that's random or on purpose? All right, on purpose. Remember I showed you that Jeep when it lost power, it was defaulted to third gear, right? If you disconnect the transmission, it loses power, you know, whatever, we blow a fuse, we want it to default in like a fail-safe mode. Why do you think we want more line pressure than less line pressure? Remember I told you, clutches slipping, wear transmission out, right? So if I had low line pressure, don't you think the clutches would slip? Don't you think that'd burn up the transmission? Don't you think it'd be better to have this solenoid default to high pressure if it loses power? And so that's why if you disconnect the transmission, you go put it in gear, it's gonna slam in gear, bam! Because it's got no amps going through SLT, and that's gonna mean high line pressure. And also it's probably gonna be default to fourth gear and forward, but in reverse is underdrive anyway. Wham, snaps your neck, okay? So if you were to see anything related to the ASE about like low milliamps of flow, that's gonna be high line pressure. If it's got high amps, that's gonna be commanding lower line pressure, okay? That stuff is on the ASE. Make sense? So the old school solenoids, we control that with a duty cycle, right? Or the old school solenoids were just on and off. The shift solenoids tend to be duty cycled. This is actually controlled more by amperage. Cool? So you'd actually have to measure the amps. You can see it on TechStream anyway. You can look in live data. It'll show you the amps. All right? Now, what I'm about to show you, I think will help you visualize it. It's not entirely accurate, but I think it'll make it help. So the pump goes to pump, right? And it goes over here to this thing, and it goes to this valve. And this valve is basically like a trap door. Cool? So if this solenoid is giving it no amps, this thing has kind of a spring right here, and it's closed. So if we have a closed door, what's our pressure going to be? Pretty high, right? But if we start running amps to it, what that does is it actually starts to make the door open a little bit. And when the door opens, the ATF drains out and it goes into the pan, okay? So picture it like a trap door. If you're not purposely opening it, the default position is closed because the spring, remember? The spring is like a trap door. The spring will close it and it'll be like, yeah, the line pressure is super high. And then it's like, no. This thing starts sending, you know, a lot of amps, and then it's like amps, the more amps. The more amps, the more the door opens and it bleeds the fluid off. Can you understand that? So essentially what I'm saying is this is like a normally closed door. If it's normally closed, that means by default your line pressure is very high. Cool? I think you should be able to get that. Now where are the solenoids at? Here are the 750. There is, let's find your SLT. I think I actually might have cut it off screen. These are SL1 and 2. No, those are S1. I cut it off screen. Your SLT is down here. Does anybody remember? Here's your SL2, and I think your SL1 is one of these. Those are the linear solenoids. S1 and S2 are on-offs. Does anybody remember what SLU was? Torque converter clutch solenoid, TCC lockup solenoid. Cool. Now here's what that looks like on the 750. Remember I showed you some shift charts. You see how there's a lot more happening here? All right, so we're going to talk about the application devices, but we're also going to talk about shift solenoids. I'm going to tell you, if I had shift solenoid S2 go bad, what would this vehicle experience? I'm going to highlight them. Would first work? first, and then it'd be like, no second? Probably generally no. You might have some instances where that sets a DTC though, and it goes into limp home, and instead it commands it to start in fourth. Make sense? But generally, if S2 were to not work, it's not that second and fourth would slip though. See? So if we had a defective C1, these would all slip or maybe be neutral. A shift solenoid means it won't even go into that gear. You'd be like first, 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 first. If it won't upshift, we're not worried about a clutch. We're not worried about a band. We're not worried about a one-way clutch. We're worried about something in the valve body is not commanding the upshift. Make sense? And an electronically controlled, forget about the governor. We're all about the shift solenoids. Check the shift solenoids, diagnose the shift solenoids. If the shift solenoid S2 is no good, that would make a lot of sense. Cool? Roberto, go ahead. Exactly. So what does a what do? Same. So remember, clutches apply and turn, or clutches apply and hold, or clutches apply and they get turned. Make sense? So like if you have a slipping clutch or a brake, right? A brake would be the same as a clutch, except it just holds it. So if I want to hold this carrier, that would be the job of a brake. But if I want to become turning the sun as an input, that would be the job of a clutch. If the clutches are slipping, you're going to have a transmission slip. On an electronically controlled, remember what I showed you, you're going to get a DTC. So if you got code set for slipping clutch or whatever, you pretty much know you got like a mechanical thing going on. Now that may be a hydraulic leak, or that may be a literal burned clutch plates, but that's not a shift solenoid. A shift solenoid is going to be like, oh, you want second? How about no? First, 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 right? It's not even initiating the shift. Now, if it tries to go to second, and second's like this, zing, and then it goes to third, it was like, what the heck was that? Second gear was just a neutral mess. You think that probably a clutch is slipping. See kind of how it's different? It's just different. Cool? And then if you were to look at this and we were to have fifth gear not work, what are your thoughts? SL1 or maybe SR. Yeah, so then we might have to do more diag. Cool? So SL2 you can see first, second, third, and fourth, but not fifth. Now let me trip you out. What if SL2 was stuck on? You see how that would mess up fifth? How the heck could a shift solenoid be stuck on? Filter wouldn't have it stuck on. Filter would be like stuck off. If the filter was clogged, fluid would never get there. That's like off. But what if that valve was messed up and it was sending fluid all the time? Don't you see how that could get stuck on mechanically? If that little valve in there were to get stuck, I don't know, maybe you could short it to ground or something too, but realistically it'd probably be more of a mechanical failure. So we could ask in different ways. What if it's stuck on? What if it's got an open circuit? That'd be like equivalent to stuck off. A closed filter would be like, a restricted filter would be like equivalent to stuck off. And then here you can see the different valves with the solenoids only. See, so this is complicated, but you should still be able to answer all of these. This question may take you 3 minutes, but again, if you knock out the basic questions, flag this one, bust out all your basic questions, and then you come back and you're kind of spent, but you're like, all right, but this I can figure out. You can figure this out even if it takes you 5 minutes. You can for sure get this question right. Whatever it asks you, the answer is in this chart. They may give you this chart, they may give you this chart. This one would be nice. Isn't this a lot more simple? Remember we were talking about S2? We need S2 in second and third, right? This is just precise. And then when we talk about how we're going to control these, again, we're using SL1. So these are linear solenoids. SL1 controls C1. SL2 actually controls B1 in this case. So how we apply clutch 1 and how we apply brake 1 depends on all these inputs to the TCM, and then the TCM will like ramp up the duty cycle fast or ramp it up slow or like customize it to make it shift exactly the same as all of the other transmissions and have the customer always really happy. That's our goal. Now here's a new chart you haven't seen. If this A750 had a shift solenoid S1 fail and it set a code for S1, this is what it will do. S1 doesn't work, so when you start out, it would initially try to give you fourth, and then it would kick you down to third because it actually switches S2 to off, right? If it was off, that's fourth. But in the computer, it says, you know what? I know what's happening here. S1's no good, so therefore manually change S2 to on. That gives you, rather than fourth, it gives you third. So you get third, third, third. And then when you're about to go into fourth, because this one doesn't work, we turn this one off. That gives you fourth, and fifth still works. So this one driving, third. Well, actually, it's more like third. Like the sound effects are free. It's going to be really slow, but then actually third, fourth, and fifth right here on the freeway, it's going to drive fine. That would be specifically employed only if it knew that there was a problem with S1 because it detected a circuit failure. Make sense? It's constantly watching for voltage drop on that circuit. Now here's the 660. Here's a bunch of solenoids. SL1, SL2, SL3, SL4, SLU, and SLT, all linears. All stuck down in here. And then SL down there. All right, here's what that looks like. Here's the chart. So if you had a defective SL, what gears would be affected? Second through sixth all the way. If you had a bad SL1, you probably only really have fifth and sixth, unless it puts it into some failsafe. And it could, right? And SL2, you'd actually be looking pretty good first, second, third, and fourth. No, first, second, and third, but starting in fourth to be affected, right? So it's really similar to how we look at the clutches. It's just when it has more solenoids, it looks a little more complicated. You just got to break it down. Roberto, go ahead. You only want to really look at what's important. Yeah. Generally, they're only going to be talking about what's in the drive range. So on the ASE, they probably won't even put this on the bottom here. That helps. But additionally, like if you look at the answer choices and all the answer choices are shift solenoid, then I wouldn't even look at the clutches and brakes. But if there's both, then I would look at both, because ultimately you really just need to pick the right answer. So sometimes I'll go at it like where I'm going to go really in detail, and then I'll be like, you know what? No, just let me look at the answer choices. Okay, I just need to figure out which shift solenoid it is, and I'll like eliminate some of it just to save time and effort. But again, flag this one, answer the stuff that doesn't take a lot of brain power. This could suck a bunch of brain power out of your mind because you got to look at a lot of stuff. But this should be a guaranteed correct answer. So I like these, but it takes more work, and that's why I kind of save them for last. I don't want to exhaust myself and then guess on the last 5 due to this. Cool? So this would be your normal control, right? Not a real big deal. And then this again talks with linear solenoids. So back in the day, we would have to use like one valve to control another valve, to control another valve, to control the brake. And now the linear valve's like, no, give it to me. I'll take the line pressure. I'll modify the pressure. I'll time it. I'll control exactly how the brake comes on. We don't need to do stuff with like accumulator control or any of that. More simple. Now the U660, if we were to have let's say SL2 off, that would do first, second, third, first, neutral, neutral, but because it goes into failsafe, instead it gives you fourth, 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 fifth, sixth. Make sense? So naturally, this car would be undrivable. But because it can monitor that, particular failure, it can go ahead and give us this. Cool. So that's really just the point there. If the transmission's not shifting the way you think, you need to check codes, because if it has a code for SL2, this is how it's going to shift because it's like a limp home. It's fail safe. Cool. Not that crazy. Here's that EPC, but now we're going to cover it as EPC. That's ASE. Remember, Toyota, SLT, ASE, EPC. Cool. Rapidly on and off. Again, it's going to be controlled either by duty cycle or it may be controlled by amps. Still does kind of the same thing. So if you look, we talked about duty cycle a little bit. This is 75% off, 25% on, because again, it's ground control. So we only care when it's grounded. That means it's on because we're controlling the ground. Cool. And you can just generally see like right here, this is, and this one's saying the other way, but most of the time this would not be true. Oh, no, that is true. Decreasing the duty cycle will increase the pressure. I read that wrong and I was like, that's a mistake I didn't catch, but it's correct. I just misread it. Decreasing the duty cycle means increased pressure. So what if you disconnect it? The duty cycle's flatline. That's maximum, maximum, maximum pressure, okay? Maximum. So another reason why we'll do it ground control too. It's a better idea. Cool, now increasing the duty cycle is gonna decrease the pressure. Cool, that's definitely critical. And here you can see we have, like in this case, this is a 10 amp fuse. Now do you guys understand what I was saying about that Jeep? If that 10 amp fuse blew, all these would be what? Off, 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 off. So what's the default for all off? I don't know, third, fourth, something like that. Make sense? They always build it so that if you lose power, it's drivable. That's why it wasn't that complex to me when I jumped in the Jeep and I'm like, oh, this feels like third. And I immediately knew, like, if you wanted, this is where you could get confused. You'd be like, oh, it's in third. Let me look up the chart and let me check this solenoid. See, but like, if it's defaulted to like a failsafe, I would actually want to check the fuse and check, really what I would check is right here at terminal E. There has been a wiring diagram on the ASE many times, a lot older looking than this, but it's like, it asks something along the lines of, what should the technician check first? And it's going to say you should check terminal A at this solenoid, or you should check terminal B at that solenoid, or you should check this, or it's like it's in limp home, it's in default mode. The most logical would be to see, is it even getting power? Is it even powering up? So E would be first. Make sense? Or you could actually go for ground. I don't know if there's a ground here. But if it was ground for the whole transmission, you might actually consider checking ground, but it's probably going to be checking power, if you will. Cool, you got it? Not that hard. Cool, now this is just to walk you through how the shift occurs, okay? I think most of it you got, but now we're going to really nail down how the electronically controlled works versus what you already learned, the hydraulic. This is a 4-1-TE. Solenoid 1 controls underdrive, solenoid 2 controls overdrive, solenoid 3 controls low reverse, 4 controls the 2-4. In first, solenoids 1 and 3 are going to be used to route the line pressure to the underdrive clutch and the low reverse clutch. So let's see what that looks like. Look at this. Fluid comes from the pan, goes through the filter, goes up to the pressure regulator, and then pressure goes two ways. One to the manual valve, and the manual valve sends it to, look at this, S1, S2, S3, and S4. Can you tell that S4 is off? Can you tell that S2 is off? How can you tell that S4 and S2 are off? Is there fluid going through? Right? I don't know if you guys can see, but I'll draw it bigger. This is 3, this is 4, this is 1, this is 2. No fluid passing through S2, right? So therefore we know it's off. No fluid passing through S4, so we know it's off. So which solenoids are on? S3, which ultimately goes and send it to, what's that thing up there? The low reverse clutch. You can see that on the camera pretty good or no? It's a little small. That's how we get the low reverse clutch filled. And then S1 does the underdrive clutch. So if you were to picture the transaxle like this, we would need S1 We would need the low reverse clutch applied, and we would need the underdrive clutch applied. Exactly what that looks like, I really don't know, but hydraulically, that's what it looks like. If you want first, you give me low reverse and you give me underdrive. Cool? That's how you get first. How do you get that? You turn on S3, you turn on S1. And you better have S4 and S2 off or you ain't gonna get that. See how simple that was? So let's go with any volunteer. How do you make first gear? How does the TCM make first gear happen? TCM doesn't control clutches, you know that, right? TCM can control solenoids, so how? Let's give 12 volts and ground to S3. Let's give 12 volts and ground to S1. Done. That's it. It doesn't have to worry about like, oh, we're going to send throttle pressure here. We're going to send governor pressure there. They're going to, you know what I'm saying? Like, it's just like, just virtually look at throttle pressure and governor pressure, know which one is winning on a virtual basis, and then command the shift solenoid. Have a nice day. Cool? Oh, you want second gear? Well, here you go. So now we got new solenoids in play. S3 is, can you tell? This is 3. What is S3? Off, right? No fluid. What is S4? Off. What is S1? On. Yeah, exactly. And S2? Off. So all we really needed, you know what? Let me take a quick look at that. Did solenoid S4 send fluid this way? It might have. It looks like 4 might have come on. 4 might have come on and sent it out this way. I didn't know really what that was. That one confused me a little. So maybe we just need 4 and 1. How did that differ from first? 3 and 1 was first. 4 and 1, I think, appears to be second. So what did you do? You left 1 on, you turned 3 off, and you turned 4 on, and there's your second gear. Here's your third gear. S3 is off, S4 is off, S1 is on, and S2 is on. Make sense? If we have S1 on and S2 on, what are they sending fluid to? Underdrive clutch and overdrive clutch. That's kind of interesting. If we overdrive one gear set and we underdrive one, what do you think the net is? We underdrive one and then we overdrive one. Don't they cancel each other out probably? Direct drive, third gear. Have a nice day. That's how you make direct drive. You don't even lock them together actually. Just underdrive one and overdrive the other, and then you get your 1-to-1. Kind of weird, huh? And then fourth, when we want fourth to occur, we're going to go ahead and we're going to turn on S3's off, S4's on, S1's off, S2's on, and then look, S2 sends the fluid to the overdrive clutch. The 2-4 clutch and the overdrive clutch combined give us fourth gear. Make sense? So it's not that different than a manual control, than a hydraulically controlled. It's just the solenoids do everything. We don't need to worry about throttle pressure and governor pressure and crap. The computer controls the solenoids control the fluid controls the application devices, and that controls the gear set, and there's your gear ratio. Cool? Not that bad. All right, and so this one's again just kind of summarizing. What we said a second ago is a little oversimplified. A lot of times, the solenoid valve actually controls a bigger valve. All right. It's cool if the solenoid valve controls the clutch directly, and a lot of the SLs do, the linear solenoids that are duty cycled, but the small basic solenoids, they more send pressure. Like this solenoid S4 right here will send pressure to here, which will move a big valve, which will actually send the fluid to the overdrive or to the underdrive or to the second or to the low reverse. Make sense? So that kind of sucks, but the way we diagnose it's still really the same. Ultimately, the solenoid controls the shift valve now. Make sense? What used to control the shift valve in the hydraulically controlled transmission? Do you recall? The throttle and the governor, and they're trying to move it. Cool. Now they eliminated those and they just poured in one solenoid pressure and the solenoid. Boom, you got it. right? And so this is just showing you first, second, third, and fourth using the relay valves, the bigger shift valves. Similar. This is just showing you a more exploded view of, let's just say you had, let's just say, for example, you had that clutch up there that was failing on you. You'd look at this diagram and you could trace it, every valve, everywhere it goes, right? Because if that clutch continues to fail, it may be because it's not getting enough pressure because it has a leak somewhere. So you'd have to troubleshoot all these things and see, is it leaking anywhere, right? This is not really the ASE type concepts. If this is what you're doing, like troubleshooting a repeat failing direct clutch, you're like top tier automatic transmission tech. That's to a higher standard than A2 certified. Right? There's very few people who actually do this, and there's a lot of people who are A2 certified. My goal, if you're A2 certified, you should be able to have an educated conversation, understand it, road test, verify the concern, and diagnose the concern, whether it's like a solenoid, a harness, a TCM, whether it's a clutch. Not necessarily be like, oh yeah, bust this diagram out and pressure test the valve body and find porosity in the valve body case. You know what I'm saying? Like, that's high level stuff. Okay? If you can do it, I'm interested. But for what we're trying to do here, it's a little over the top. All right, and then this talks a little bit about the TCM. So how does the TCM work? It's going to look at memory. It's going to process information. It's going to deal with input sensors. And then it's going to do output drivers. So the engineers are pretty smart, smarter than me, but they're copying. This has been done before. Can you think of anything that kind of resembles this? Who? Whoa, why did you just react right there? Toss it back. Okay. So you demonstrated to me, you used your inputs, right? Your sight, you saw the marker, you thought about it. You were like, oh, that's going to hit me. Make sense? Your brain is the processor. Your brain processed through your sensors of your eyes, and then it said, you know what, I should prevent this. Contract this muscle, contract that muscle, open this, do this, right? So the engineers are smart, but really they're kind of copying the body, if you think about it. It's pretty hard to find somebody who has a genuinely original thought. They're mostly kind of like copying and pasting, sort of. So it's just like your brain. The computer's your brain. You're going to process information. See, you threw it at me, and I pretended like I had either, maybe I couldn't see. If I was blind, you'd have felt bad, huh? If I had something wrong in my brain where my response was too slow, you'd even feel bad. But see, I just played along. I saw it. I knew it was going to hit me. I just didn't stop it. But I thought about it. If I had defective programming from the factory, I could have just got hit in the face with a marker. Make sense? So the computer's only as good as its programming. You guys got to understand that. If the programming is defective, the outcome is going to be defective. It needs the correct software to function. Okay? The rest of this is mostly going to be hardware. If you have a defective sensor, like if I was blind, I have defective sensors, I'm not going to catch the marker. If I had some sort of a problem in my nerve, that's like a wire, right? My brain sends a signal in my nerve to move my arm and to catch that thing. If I had a problem in that nerve, it wasn't going to work, right? So when you think about troubleshooting these systems, just kind of remember the inputs are the sensors. Those are the senses. The computer is the processor, and that can have bad software, although not real likely. And if it does have bad software, that'd be likely part of a TSB. There'd be a TSB out there. And then the outputs are going to be the muscles. They do the work, but you got to get a signal to them. And the nerves, by the way, work both ways. Your eye sends a signal through your nerve to your brain. And then your your brain sends a signal through your nerve to your muscles to block it, right? So the nerves are the wiring. Cool? And then as you remember, the DTC, the ECM can Retained DTCs, freeze frame, which we talked about a second ago. When a DTC sets, it can store freeze frame. That'll take a snapshot of all the conditions that were at that moment. So if it set a DTC and you look on freeze frame and you see it's at wide open throttle at 104 degree ambient temperature, the transmission fluid is 240, like you know that's hot and at wide open throttle, and the vehicle speed, this one's for Brandon, is 147. Like, I know what you've been doing. That gets logged when that code sets. Make sense? So if one of our steps is to duplicate the concern, I may stop and go to the customer and say, hey, you got a concern, I want to fix this for you, but I looked at your freeze frame and you were doing 147 miles an hour and everything on the car was hot. I can't duplicate that for you. Well, I want you to duplicate it. No problem. Let's start by filing a police report and then I'll duplicate it. You get the police to give me permission to drive it at 147. You know what I'm saying? Like, you could kind of play the game. But the point being, that's kind of a joke. The point being, if you want to duplicate an intermittent concern, get the freeze frame, and then you know how you should be driving it to maximize your chances of duplicating the intermittent. And then you can even see, like, when it says learn data, that a lot of times will tell you in a transmission, is it using those SL solenoids to increase your clutch volume index? Because you can actually see that it's adapted and adapted and adapted and adapted. That can give you a pretty good indication that, hey, that clutch is wearing. The more it adapts, that's probably because the clutch is worn more. You can actually see that. Okay, and then PCM and TCM can be separate. Sometimes the PCM control, it combines engine and transmission together. A lot of times they're on the CAN network, right? So we've talked CAN network before. Just know, if you see a diagram and you see engine over here, transmission over here, and then you see a CAN high and low going between the two, that just means they're communicating on the CAN network. So if you want to know engine coolant temperature, we don't have to send engine coolant temperature to transmission. We can just send engine coolant temperature to engine, then engine can multiplex that on the CAN network to transmission. Make sense? What's happening, Russ?
I shut the doors down. Nobody was there.
Okay, I'll take care of it.
Yeah, it's closed. All right.
Nice talk. See ya. Cool. So if you have a problem with a sensor that's over here in the ECM, the transmission can still, get access to that information, right? So sometimes you might have diagrams with other modules on it. I'll give you a really clean example. Vehicle speed, a lot of times goes to the ABS module. Then the ABS module will use CAN high and low to get over the TCM. If you got on a scan tool and you hooked it up and it had no communication with the ABS module, that TCM will probably not upshift. Remember that story I told you on the third transmission? That's what I'm thinking just in my mind, probably what's up. That vehicle may have a bad ABS module. Sound familiar, huh, Renee? If the ABS module is no good, it's not getting vehicle speed and it's not multiplexing it out to the TCM. The TCM may not upshift because it can't tell what speed it's going. Make sense? So you also have to understand a little bit about the network too. But it's not really that complex. If you can't communicate with the ABS module, you got to troubleshoot the ABS module. Do not put a TCM in it. Do not put a transmission in it. Fix the ABS problem. They're related. Cool. And then processor processes information. It looks at data maps. So if I pulled up HP tuners, you could see my shift chart and I can tweak it. And that will rewrite the map. And that will change what it's determining the necessary actions to be. Delay the shift, move the shift one way or another. And then generally, output drivers control those solenoids. So if a solenoid isn't working, it may be the solenoid, it may be the wire, but also remember, there is drivers, and those are basically transistors in the TCM. That transistor has to pulse ground to that SL1. If the transistor is bad, that's a bad driver, how would you diagnose that? Probably do duty cycle, would I say? If you did duty cycle and it was a flat line, and you did duty cycle coming out of the ECM and it was a flat line, and you even went in active tests and you tried to command it on, it was still a flat line, you got pretty good reason to believe the ECM it's not running its driver, it's not pulsing its transistor. And unfortunately, we can't really service those. That's in the ECM or the TCM. Cool. So that's all in there. And then again, PCM is going to monitor the TPS and the VSS, and that's going to determine the shifting points. I think you mostly got that one. If you're a more conservative driver, the transmission, the TCM will kind of learn a little bit how you drive. And if you're a more aggressive driver, it can learn a little bit how you drive. Because remember, it's constantly adapting. Mostly in Toyota's case, they're just trying to get them to shift consistently. But it can shift a little bit different too, especially on some other ones. Okay, and then again, they can have different drive modes. So if you want firm shifting, you might be able to put it in sport mode if it's a higher end car. Cool. And here we got some different drive modes. This was for power. That'll hold you in gear longer. That'll hold your shifts closer to higher RPM. Bad for fuel economy though. Bad for fuel economy. And this one's different. This is not really A2, but remember, in hybrid, which we're going to cover, they work a lot different, but they can also include regenerative braking. So if you pull this over and pull down, that's B mode. That's going to increase your regen braking. So it gets a little tricky there. All right, cool. And we're getting fairly close. What about if you're in wheel slipping? If you're wheel slipping, the transmission can function differently. So let's say that you hit a bunch of snow. What do you think that you want the engine to have more power or less power? Generally less, because you're going to spin more, right? So they can cut power at the engine, but it can also make your shifts earlier and softer too. So there are some that would look at your vehicle speed, your wheel speed sensors, and if you're slipping a lot, it might say, whoa, we're going to go in snow and ice mode and like soften the shifts a lot. I'll just say, if there you are at Big Bear and you're kind of like me when I came in here this morning, most of you guys don't know, but when I came in, I stuck it pretty hard on the turn in Cypress Circle, and I got into the wet spots where the sprinklers, spray the blacktop, and totally dead sideways on my bike. So bad where it leaned so low it stalled because the tip switch. So like, kind of stupid, but let's just say it was a car, but I didn't dump it. Okay, just full transparency. If it was a car and you hit snow and the 1-2 shift was hard, what do you think will happen? You totally lose it, right? So if you're in the snow, you want your shifts to be as soft as possible. I should have hit my second gear a little softer coming into Cypress Circle, but I didn't. But I learned, and I still want to talk to the guy who was behind me because I'm telling you, he saw something this morning. Let me tell you what. Okay, kind of makes sense? That's all happening in the ECM. And then again, if it's detecting a fault, there will be an action. So you get a customer car, the customer may say, oh, my concern is it bangs going into reverse. Well, it may only be banging going into reverse because it's in some sort of a protection mode, right? So like, you guys had cars that had transmission fluid temperature faults? Transmission fluid temperature faults made a bang in reverse. Did you expect it to? I don't know. But as a fail-safe, it will. It'll say, I don't know what the transmission fluid temperature is, so therefore, max line pressure. Bam. Cool, so just remember, if it detects a fault, it'll set a code, but it also may take a protective action that can make it drive a little different. It can also turn on the mill. That could be the check engine light on most. Sometimes it'll actually give you a service transmission message. Cool? And we talked about this one, I think, pretty good. You guys understand why we look at input and output speed? Remember? It's going to determine the gear ratio, which has to do with the slipping clutches and bands. I wanted to hit that one early while I had full attention. And then torque management, we talked about a little bit too. If they know your 1-2 shift being really hard is going to damage some things, the torque management program can actually chill that out a little bit to protect itself, to make it last longer. Now, if you take it to the tuner and you tell the tuner you want the car to be as fast as possible, what do you think the tuner is going to do? Erase all this torque management. Clear that all out of there. Give it full power. Now, what would that do to your warranty? Obviously, that would be voided. And you can see why. They know that transmission might not take that full 1-2 shift at 100% power. So they torque manage it. Tuner goes in and says, nah, just give it the beans, as they say. Okay, if it breaks, that ain't covered. And if you're working on it, you may need to consider this like, hey, I'm fixing this transmission, but the failure is kind of weird, and you found out they have a tune. Maybe you do the fix, like Rigo, for example, was doing a lot of those SoCal sport truck donut trucks, and he'd rebuild the transmissions, and they'd come back like in a month totally nuked. And then he'd like look at the truck, and he'd start scrolling social media and see the truck doing donuts so much where it was lighting the tires on fire, and they'd be like, well, it's under warranty. And now if he sees one of those, he just says, I'll build it, this is the deal, but there's no warranty, take it or leave it. Because there is a limit to what you can do to a transmission. You can damage it, right? And they have their trucks all tuned, all the torque management's off. There's no protections for that transmission. And also, it's kind of hard to keep a transmission cool when you're doing like basically a stall test permanently with your back tire just barely turning. And how much air is flowing through the radiator? Nothing. And how much is that air cooling your transmission cooler, which would be in the radiator? Not much, right? So some of these electronic protections, they probably should be there if you want it to last. If you want to take it off, go for it, but don't be surprised. And then similar, you may call it limp in or limp home. That's what we were talking about. If there's a fault, it may command at 4th gear max line pressure. That would be like kind of the default. Cool, and that's pretty typical. And this is where it says EPC will mechanically default to max line pressure. Remember that? The trap door is closed, so the line pressure is high. And also, it'll illuminate the mill, so the customer's like, hey, I got a light on, and by the way, my neck hurts, but also I got a light on, so I'm bringing it in for service. And now here's that adaptive transmission control. So this is kind of like how it's saying, it's going to adapt the programming as the transmission wears, right? So as that 60 thousandths clearance gets to be 100, it's going to fine tune the shifts to make it feel as good as possible for as long as possible. And it can also change how the customer drives it. And here you can look at some different readings, like your 1-2 shift time at 0.63 seconds. Let's say the goal is 0.63 seconds. Let's say the goal is let's just say the goal is 0.50 seconds, a half a second, right? But the 1-2 shift time here, you can look on the scan tool, is at 63. What's up with that shift? It's not about the timing, it's how long it took. So this is when first let's go and second comes in. We want it to take a half a second, but it took 0.63. That's too long, right? It should drop first and pick up second in a half a second, and now it's taken too long. So what could we do to bring that down? Increase, like we take that linear solenoid and say, hey, come on a little quicker. Let's duty cycle that up higher. Rather than doing 50% duty cycle, let's jump right to 60, right? But then as the clutch wears, guess what's going to happen? It's going to jump to 70. And then as the clutch wears more, what's going to happen? 80, 90. By the time it goes to 100, if this time is still over 50, is still over a half a second, you know what it sets? It's going to be like shift delayed, but maximum pressure adapt value reached. Or it'll say something along the lines of maximum pressure adapt, but still slipping. Something like that. So that's just saying it's adapted, but now it's adapted all the way and it still can't bring it in time. That's just a really good indication that the transmission is slowly but surely wearing. That's what kind of sucks about new transmissions, is like on an old transmission, you could feel it when it started to fail. On a new one, it'll just adapt so it feels perfect until bang, your light comes on. Cool. So generally, if your light's not on and no codes are set, your electronically controlled transmission's probably fine. Probably. Cool. So that's what it says about TAP. Transmission adapt pressure, or they will call this like the clutch volume index. Kind of similar. So this one just happens to be GM. So this one even would break down into different cells. It'll actually show you, where it's at in the adaptation process. You can even tell if it's getting close to max. If you really wanted to know, you could tell if this transmission's almost worn out. Cool. And then remember, when we do the replacement, you have to reset that for it to really function. So that's a mandatory step. You got to remember to do that. And see, here's Chrysler's clutch volume index. It's showing the numbers. So you can see, actually, the overdrive clutch has got a pretty high adaptation number. That'd be a little bit concerning. 51 on the low reverse, and you got 74 on the overdrive clutch. That's getting up there a little bit. So it's trying to adapt to make it shift right. Cool. Kind of makes sense. And I think overall we're pretty good. And here's the reset. You can go in and you can say transmission adapt pressure reset. Do you wish to continue? And this is just saying you should really only do this if you replace the transmission. But there had been some times where transmission comes in, it's shifting weird. And I'm like, all right, as a baseline, let me hit reset. And if it fixes it, cool. And if it doesn't, well, this one didn't really cost anything. So you could do that. All right, you guys made it. Now, yeah, Madi, you can pause it for a second.